66 billion times the mass of the Sunday. That is the best estimate for the black hole at the center of a quasar called TON 618. Its event horizon, the boundary past which nothing returns. Not matter, not light, not information, is a sphere with a radius of roughly 1,300 astronomical units. 1 astronomical unit is the distance from the Earth to the Sunday-Neptune orbits at 30. If you set this black hole down where the Sun is now, the darkness would close over Mercury and Venus and the Earth, over Mars and the asteroid belt, over Jupiter and its moons, over Saturn and its rings, over Uranus and Neptune, over the Kuiper belt and everything in it, and it would keep going. It would keep going out past the scattered disk, into the region where the comets with 1,000-year orbits spend most of their lives. Light needs 7.5 days to travel from the center of that sphere to its edge, 15 days to cross it end to end, 2 weeks, at the fastest speed the universe permits, simply to traverse the dark. What we actually see is not the black hole. It is the gas falling into it, a flat disk of matter, spiraling inward, heated by its own friction until it glows across the ultraviolet and the optical. That disk outshines every star in its host galaxy combined. To keep it burning, the engine converts roughly 1 Earth's worth of matter into pure light every 13 seconds. The light from that engine has been traveling toward us for 10.8 billion years. It left when the universe was 2.9 billion years old, a fifth of its present age. The Sun did not exist. The Earth did not exist. The elements that would eventually make both of them were still being assembled inside stars that have long since died. That is the number. This is sidereal. And tonight we are going to stay with it. If you would like more nights like this one, a subscribe helps more than you would think. And leave a comment telling me where you are listening from and what time it is where you are. I read them when I cannot sleep. Here is what I want to give you tonight. Not just the number, but the whole chain that produced it, a photographic plate developed in a darkroom in the mountains of Puebla, a radio telescope in a field in northern Italy, a spectrum taken in West Texas by an astronomer whose name almost nobody says, and finally, a spectrograph on the summit of Mauna Kea. 4 instruments, 5 decades, and a piece of arithmetic that rests on assumptions nobody has ever been able to test directly. By the end, you will know how the number was made. You will also know how much of it we actually know. Those turn out to be 2 different questions. TON 618 is not a star. It never was. The name is a leftover from a night when nobody could tell the difference. It sits in the constellation Canes Venatici, the hunting dogs, a small and undramatic patch of northern sky between the handle of the plough and the bright star Arcturus. There is nothing to see there with the naked eye. There is nothing to see there with a small telescope. At around magnitude 15.9, it is roughly 4,000 times fainter than the dimmest star a person with good eyes can pick out on a dark night. You would need a serious amateur instrument and a very clear sky to register it at all, and if you did, it would look like a star, a faint one, slightly blue. What it is instead is a quasar, a quasi-stellar object, the blazing nucleus of a galaxy so overwhelmed by the light of its own center that the galaxy itself has never been seen. Nobody has photographed the stars of TON 618's host. Nobody knows its shape, its size, or how many stars it contains. The nucleus is several hundred times brighter than everything around it, and at this distance that glare erases the rest completely. We know there is a galaxy there because black holes of this kind do not exist outside galaxies. That is the entire basis of our knowledge about it. The engine at the center of that glare is what we are here for. Let me put 66 billion solar masses somewhere you can hold it, because on its own it is only a word followed by a word. At the center of our own galaxy there is a black hole called Sagittarius A star. We have measured its mass with unusual precision by watching individual stars orbit it for more than 20 years and fitting their paths, genuinely watching them swing around an invisible point year after year. The way you might chart a comet. It comes out at about 4.1 million times the mass of the Sunday. That is the black hole our entire galaxy turns around. Every star you have ever seen with your own eyes is in orbit, at some remove, about that object. TON 618 is roughly 16,000 times heavier. Try a bigger one. In April of 2019, A collaboration of radio observatories spread across the planet published the first direct image of a black hole's shadow, the dark center of the galaxy M87, 55 million light-years away, in the Virgo cluster. That image took years of coordinated observation and a specially built computational pipeline to produce. The object it showed weighs about 6.5 billion suns, and at the time, it was among the heaviest well-measured black holes known. TON 618 is about 10 times heavier than that. Now step back further. Take the Milky Way, not the black hole at its center, but the galaxy. All of it. Every star in the disk, every star in the bulge, every star in the halo, the ones we can see and the vast majority we cannot, spread across 100,000 light-years of space and assembled over more than 10 billion years of continuous star formation. Add them up. The total stellar mass of this galaxy is something close to 60 billion times the mass of the Sunday, which means that if you put every star in the Milky Way on one side of a balance and this single black hole on the other, the balance would sit roughly level. I want to be careful here, because this comparison gets mangled constantly. The Milky Way's total mass, including its dark matter halo, is more than 1 trillion solar masses 20 times greater than TON 618, and no contest at all. The comparison that actually holds is with the stars alone, but that comparison is the interesting one anyway. Stars are the thing the universe took its time over. They form slowly, from cold gas, in a process that has been running in this galaxy for something over 13 billion years and is still running now. And what all of that produced, in total, is matched by one object that finished assembling itself before the universe was 3 billion years old. That is the shape of the problem we will spend part of tonight inside. The distance is the other thing worth setting down early, because it has a subtlety in it that most accounts skip. The redshift of TON 618 is 2.219. That number means that every wavelength of light coming from it has been stretched by a factor of 3.219 on its way to us. A spectral line emitted at 4,861 angstroms in the blue arrives here at 15,600, deep in the infrared, invisible to the eye and to ordinary optical detectors. The stretching is not motion through space in the ordinary sense. It is space itself expanding underneath the light while the light is in transit. Put that redshift into the standard cosmology, and the light comes out as having traveled for about 10.8 billion years. That is the look-back time, and it is the number that matters for what we are seeing. We are looking at this object as it was 10.8 billion years ago, and we have no way, ever, of knowing what it looks like now. But here is the part that gets left out. Because the universe has been expanding the entire time that light has been in flight, TON 618 is not 10.8 billion light-years away today. It is roughly 18 billion light-years away today. The light took a shortcut through a smaller universe and arrived in a bigger one. If you sent a signal back along the same path this evening, it would never arrive. The expansion between here and there now outruns it. So the object we are discussing is, in a real and permanent sense, out of reach, not merely far, causally disconnected. Whatever TON 618 is doing at this moment, still burning, or long since starved and gone quiet, its black hole, sitting cold and enormous at the center of a galaxy full of dying stars, is not information that can ever reach this planet. We have the photograph. We will never get the follow-up. Now, the light itself. The bolometric luminosity of TON 618, the total power it radiates, integrated over every wavelength from radio to X-ray, is approximately 4 times 10 to the 47th ergs per second. And there is a tiny unit, roughly the energy a mosquito spends flying. 10 to the 47th of them per second is about 140 trillion times the output of the Sunday. You can hold that a different way, through the fuel. Mass and energy are the same currency, and the exchange rate is the speed of light squared. To radiate at that power, the accretion disk has to be converting matter into radiation at a rate of about 440 billion tons every second, which is 1 Earth's worth of rock and iron, entirely annihilated roughly every 13 seconds. But that is only the fraction that becomes light. An accretion disk is efficient, though not perfectly so, Something like 10% of the rest mass of the infalling gas gets converted to radiation before the rest disappears past the horizon, which means the total amount of matter this black hole is actually swallowing is about 10 times higher than the amount it is turning into light. Run the arithmetic, and it comes to something on the order of 70 solar masses per year. 70 stars a year. Not their light, their substance, gone across the horizon, added to the mass, never to be seen again. And here is the thing that surprised me when I first worked through it, and that almost nothing written about this object mentions. There is a hard ceiling on how brightly an accreting object can shine. It is called the Eddington limit, and we will come to how it works. What matters now is the number. For a black hole of 66 billion solar masses, that ceiling sits at about 8 times 10 to the 48th ergs per second. The observed output is 4 times 10 to the 47th. TON 618 is running at something like 5% of its maximum. Take the mass estimate down to the low end of its uncertainty, and the figure rises, perhaps to 15%. It does not get close to the limit under any reading. The most massive black hole we have ever weighed is not the hungriest. It is not straining, not tearing at its surroundings, not consuming at the edge of what physics allows. It is idling, 70 suns a year, at a fraction of what it could take if the gas were there, and it is still producing more light than 100 trillion stars. Whatever built this thing is not what we are watching. We arrived late. The construction finished long before the light we are reading left the disk, and what we are seeing is the aftermath, an enormous object, comfortably fed, in no particular hurry, shining out across 2/3 of the age of the universe, because it has nothing else to do with the energy. Which brings me to the number one more time, and to the thing that this entire night is really about. 66 billion solar masses is not a reading. There is no instrument that was pointed at TON 618 and returned that figure. Nobody weighed it. What happened is that in 2004, a group of astronomers took a single infrared spectrum, measured the width of one hydrogen emission line, fed that width into a formula calibrated on much smaller and much closer objects, and got a number out. The formal uncertainty on that number is about a factor of 2.5 in either direction, which means the honest statement is this: the black hole at the center of TON 618 has a mass somewhere between roughly 20 billion and roughly 200 billion times the mass of the Sun, and 66 billion is the middle of that range. 20 billion and 200 billion are not close together. The lower figure would still make it one of the largest black holes ever measured. The upper figure would make it larger than any theory of black hole growth comfortably permits. Both are inside the error bar. Neither can currently be excluded. That gap is not a failure of the astronomers who published it. They stated it plainly, in the paper, in the table, next to the number. It is what happens when you push a measurement technique to the very edge of the range it was built for, and honestly report what comes out the other side. But the gap did not survive the journey out of the journal. What survived was 66 billion on its own, without the range attached, and that is the version that reached the rest of us. So the question tonight is not only how big this thing is, it is how anybody could possibly know, and what it means that a number can be simultaneously the best available answer and a very rough guess. To get there, we have to start at the beginning, and the beginning is not a black hole at all. It is a dark room in Mexico, a sheet of glass, and 2 men with a microscope who had no idea what they were looking at. The plate is 8 inches by 10, a sheet of glass with a gelatin emulsion of silver halide crystals spread across one face. It is not a photograph in the sense you are used to. Nothing about it is designed to be looked at directly. It is a detector, a chemical surface engineered to record, permanently and measurably, the arrival of light. On the night it was exposed, in 1957, a shutter opened above a mountain in central Mexico, and photons that had been in flight for 10.8 billion years came to rest in a few grains of silver. The observatory is Tonantzintla. It sits a few kilometers outside the city of Puebla, in the volcanic highlands southeast of Mexico City, at an altitude of a little over 2,000 meters. The name comes from Nahuatl and means, roughly, the place of our little mother. The observatory exists because of one man's stubbornness. Luis Enrique Erro was a Mexican politician, diplomat, and amateur astronomer who became convinced in the 1930s that his country needed a research observatory of its own, and who then spent years extracting the money and the political support to build one. He was going deaf at the time, a progressive hearing loss that would eventually be total, and he carried on regardless, corresponding with astronomers at Harvard, securing an instrument, choosing the site for its thin, dry air and its stable nights. Tonantzintla was inaugurated in February of 1942, in the middle of a world war, with astronomers from the United States traveling down to attend. The instrument at its heart was a Schmidt camera. That design deserves a moment, because it is the reason this story is possible at all. An ordinary telescope has a narrow field of view. Point it at the sky, and you see a small patch, sharply. And to survey anything large, you must take thousands of exposures and stitch them together. The Schmidt design solves this with a trick: a spherical primary mirror, which has no preferred axis, and therefore no edge of field distortion, paired with a thin corrector plate at the front of the tube, whose surface is ground to a subtle and complicated curve that precisely cancels the spherical aberration. The result is a camera that can photograph an enormous field of sky with sharp star images from the center right out to the corners. The Tonantzintla Schmidt had a corrector plate about 70 centimeters across and could capture a patch of sky 5 degrees square on a single plate, an area large enough to hold 100 full moons. It could record stars down to around 18th magnitude. It was not built to examine individual objects in detail. It was built to collect, in bulk, and to make catalogues. The man who ran the scientific program was Guillermo Haro. Haro is one of the more interesting figures in 20th century astronomy and one of the least discussed outside Mexico. He came to the subject sideways. He had studied philosophy and law, worked as a journalist, and only turned to astronomy in his mid-20s, teaching himself the fundamentals and then training at Harvard before returning home. He had an unusually good eye for the anomalous. In the 1940s, he identified small, strange, glowing knots of nebulosity near newborn stars that did not behave like ordinary nebulae. George Herbig, working independently in California, found the same objects, and the two names were joined together on them permanently. They turned out to be shock fronts, places where jets fired from forming stars slam into surrounding gas at hundreds of kilometers per second. He also catalogued flare stars in the Orion region in numbers nobody had expected. His method was comparison. Photograph the same field twice, once through a filter sensitive to blue light and once to red, and lay the plates side by side. A star that is prominent on the blue plate and faint on the red is hot. A star that is prominent on the red and faint on the blue is cool. Anything that behaves oddly across the pair is worth a second look. It is a simple technique, and in the hands of someone patient, it is remarkably powerful, because it converts a question about physics into a question about which of two dots is bigger. Haro's own story continued well past this survey, and it is worth a moment because it explains why the plates still exist. He became director at Tonantzintla, and he was the first Mexican elected to the Royal Astronomical Society. More importantly for what came later, he spent much of his career building institutions rather than only using them. He was central to the founding of the National Institute of Astrophysics, Optics and Electronics, which grew out of the Tonantzintla Observatory and remains one of Mexico's principal research centers. He was married to the writer Elena Poniatowska, one of the major figures of 20th century Mexican letters. The reason this matters to a plate archive is dull and decisive. Institutional continuity is what preserves glass. Observatories that were absorbed, defunded, or closed have lost their collections repeatedly, to damp, to building work, to somebody needing the storage space. Observatories with a permanent institution attached tend to keep them, and in recent decades many of those collections have been catalogued and digitized, which means the century of sky recorded on emulsion before electronic detectors arrived is still available for comparison with the sky now. That turns out to be scientifically valuable in a way nobody anticipated when the plates were exposed. If you want to know whether an object has varied over 70 years, there is exactly one place to look, and it is a cabinet. In the 1950s, Haro's group ran a systematic survey of the northern sky for faint blue objects. At that time, the category faint blue object was a genuine grab bag, It contained white dwarfs, the collapsed cores of dead stars, hot and small and blue. It contained hot subdwarfs. It contained the occasional oddity nobody had classified. There was no expectation that it contained anything extragalactic, because point-like sources of light were, by definition, stars. That was not a hypothesis. It was the meaning of the word. The plate inspection fell to two younger astronomers, Braulio Iriarte and Enrique Chavira. I have not been able to find much written about either of them, which is itself part of this story. Iriarte joined Tonnant-Sintler in the early 1950s after training in physics and mathematics. Chavira arrived not long after. Between them, over years, they worked through an enormous quantity of glass. Picture the actual labor: a darkened room, a plate laid on a light box or held against an illuminated screen. A low-power microscope or a magnifying eyepiece moved slowly across the emulsion in a grid pattern so that no region is missed. The plate is a negative. The sky is a field of developed silver, dark and slightly grainy, and each star is a small clear dot where the emulsion was exposed and then washed away in the fixer. Brighter stars make bigger dots. The dots are not images of the stars are unresolvable points, infinitely far as the optics are concerned. They are records of how much energy arrived, spread by the atmosphere and the emulsion into a small disk. For the survey that produced TON 618, the plates were taken with a thin prism mounted in front of the telescope. This turns each star from a dot into a tiny streak, a spectrum, perhaps a millimeter long, in which the star's light has been spread out by wavelength. The eye cannot read detail at that scale, but it can read shape. A hot blue star produces a streak that is dense at one end and thin at the other. A cool star does the reverse. An object with an unusually strong ultraviolet continuum stands out on the plate as visibly wrong compared to its neighbors. So Iriarte and Chavira went through field after field, looking for streaks that were wrong in the right way, and when they found one, they measured its position and gave it a number. The numbering was sequential. There was no ranking, no significance, no flagging of the interesting ones, just the next integer. Number 618 sat at right ascension, 12 hours, 28 minutes, declination plus 31 degrees. It was well away from the plane of the Milky Way, in a direction that looks out through the thin part of our galaxy's disk and into the universe beyond, though nobody at the time drew any conclusion from that. Its magnitude was 15.9 in the blue. Its image was stellar, no fuzz, no surrounding haze, no hint of extended structure. Under the seeing conditions available on a mountain in Puebla, it was a point. That is what a star looks like. The description, if one was written at all, would have said something like stellar. Then the eyepiece moved on, and the next object became number 619. The list was published in the bulletin of the Tonnant-Sintler and Tacubaya observatories, a small journal in Spanish with limited circulation. It was read by the people who cared about peculiar stars and by almost nobody else. The name TON 618 is simply the abbreviation of the observatory plus the entry number, a convention shared by dozens of survey catalogues of the era. I want to sit with the physical object for a moment because it still exists, or at least it may. The plate was manufactured somewhere in the United States, coated on glass, sealed in a light, tight box, and shipped to Mexico. It had to be kept cool and dry before use because emulsions degrade. It was carried up to the telescope, loaded into the plate holder in darkness, exposed for something between half an hour and an hour, while the drive tracked the stars, carried back down, developed, fixed, washed, dried, and filed in an envelope in a plate library. Emulsions crack, silver oxidizes, glass breaks. Plate archives around the world have been lost to floods, fires, building works, and simple institutional indifference. But many survive, and the Tonnant-Sintler collection is among those that have been actively preserved and, in recent years, digitized. So there is, in all likelihood, a sheet of glass in a cabinet in Mexico with a small cluster of silver grains embedded in its surface. Under a microscope, those grains are irregular black specks, of no obvious interest, indistinguishable from 100,000 others on the same plate. They are also the physical terminus of a journey. The energy that reduced those silver ions to metal was released by gas falling toward a black hole when the universe was 2.9 billion years old. It crossed 10.8 billion years of expanding space. It passed through the Earth's atmosphere, through a corrector plate ground by hand, off a spherical mirror, and into a gelatin layer a few microns thick, where it stopped. Nothing about that was recognized. The plate was filed. The list was published. The entry sat there. For 13 years, Ton 618 was a blue star. Not a mystery, not a candidate, not an anomaly awaiting explanation. A blue star, number 618, in a catalogue of blue stars, in a journal few people read. And the reason nobody noticed is not that these astronomers were careless. It is that in 1957, the correct answer did not exist yet. There was no category into which this object could have been placed. Karl Schwarzschild had solved Einstein's equations for a point mass 41 years earlier, and Oppenheimer and Snyder had described gravitational collapse in 1939, but those were mathematical results about extreme hypotheticals. The idea that such objects sat at the centers of ordinary galaxies, eating gas and shining brighter than everything around them, was not a minority position. It was not a position at all. The word quasar would not be coined for another 7 years. Iriarte and Chavira found exactly what they were looking for, which was a faint blue object, and they recorded it correctly, and they moved on. The discovery was made and simultaneously not made. It was sitting in print, with coordinates accurate enough to point a telescope at, waiting for a framework that had not been invented. That framework arrived from an entirely different direction, and it did not come from optical astronomy at all. It came from a group of physicists who had spent the war building radar, and who came out of it with equipment, expertise, and a very strange new map of the sky. The radio sky was discovered by accident, by an engineer who was not looking for it, and who never got to follow it up. In 1932, Karl Jansky was working for Bell Telephone Laboratories in New Jersey on a practical problem. Transatlantic radio telephone links kept being spoiled by static, and somebody needed to find out where the static came from. He built a rotating antenna on a set of wheels salvaged from a Model T, aimed it at the horizon, and spent months tracking hiss. Most of it turned out to be thunderstorms, near and distant. But there was a residue he could not account for, a faint steady signal that rose and fell once a day, and not quite once every 24 hours. It came back 4 minutes earlier each day. 4 minutes a day is the signature of the stars rather than the Sunday. Jansky worked out that the source was fixed against the celestial sphere, and that it was strongest when his antenna pointed towards Sagittarius, which is the direction of the center of the Milky Way. He published. The New York Times ran a piece, and then Bell Labs, having answered the question it cared about, moved him on to other work, and he never studied the sky again. For most of a decade, the field consisted of one man, Grote Reber, an engineer in Illinois who built a 9-meter parabolic dish in his back garden with his own money and mapped the radio sky essentially alone. Then came the war, and with it an enormous acceleration. Radar research put sensitive receivers, waveguides, and antenna theory into the hands of thousands of physicists. And when the war ended, a great many of them found themselves with the skills, and often the surplus equipment, to point that technology upward. In Britain, the two centres were Jodrell Bank in Cheshire and the Cavendish Laboratory at Cambridge. The Cambridge group was led by Martin Ryle, who had spent the war working on radar countermeasures and who brought to astronomy a genuinely new idea. Instead of building one enormous dish, connect several smaller ones and combine their signals so that the resolving power depends on the distance between them rather than the size of any one. This is interferometry, and it is the reason we have images of black hole shadows today. Through the 1950s, the Cambridge group produced a series of surveys. The third of them, the third Cambridge catalogue, appeared in 1959 and was revised in 1962. It listed several hundred discrete sources of radio emission across the northern sky, each with a position and a flux. Most of them, once optical astronomers went looking, turned out to be things that made sense. Supernova remnants, the expanding debris of dead stars, threaded with magnetic fields and full of electrons spiraling at relativistic speeds. Clouds of ionized hydrogen. and a good number of galaxies, some of them peculiar, with radio emissions spilling far beyond their visible starlight. But some of the brightest sources in the catalogue had no counterpart at all. They were point-like in the radio, which meant compact. When the position was good enough to search optically, astronomers with large telescopes went and looked, and they found either nothing or a faint star. And when they took a spectrum of that star, it was wrong. A stellar spectrum is a continuum crossed by absorption lines, dark gaps, where atoms in the star's outer layers have removed specific wavelengths. Those lines are how we know what stars are made of and how hot they are. The whole apparatus of stellar astrophysics rests on reading them. These objects had no such lines. Instead, they had bright emission lines, sitting at wavelengths that matched no element anybody could identify. The strongest case was an object catalogued as 3C48. Thomas Matthews and Alan Sandage found its optical counterpart in 1960, a 16th magnitude blue point. Jesse Greenstein at Caltech took its spectrum and could make nothing of it. The lines were broad, strong, and at positions with no known match. Greenstein spent a long time on it and eventually published a paper suggesting the object might be some new sort of star, possibly with unusual physics near its surface. He was, as he later put it himself, looking straight at the answer and unable to see it. The problem was resolved by geometry, and specifically by the Moon. 3C273 was the brightest of the unexplained radio sources. Its position was known, but not well enough radio positions. In the early 60s were typically good to an arc-minute or worse, and an arc-minute of sky contains a great many faint stars. Cyril Hazard realized that a much better position could be obtained without any improvement in the telescope, simply by waiting for the Moon to pass in front of it. The technique is beautifully simple. The Moon's position and motion are known to extraordinary precision. When its limb passes across a compact radio source, the signal cuts off abruptly, and when the far limb passes, the signal returns. Time those two events, and the geometry gives you a position accurate to a fraction of an arc-second. 3C 273 was occulted 3 times in 1962. Hazard organised the observations at the newly commissioned Parkes Radio Telescope in New South Wales, a 64-metre dish in a sheep paddock. Getting the measurement required pointing the dish below its designed elevation limit, which meant John Bolton, the observatory's director, personally overseeing an operation that involved the telescope's structure being pushed past what the manual permitted. They got the data. The position led straight to a 13th magnitude blue object. It also revealed something else, a faint wisp of light extending away from it, which we now know to be a jet of plasma thousands of light-years long, launched from the nucleus at very nearly the speed of light. It is visible in amateur images today. The spectrum was taken with the 200-inch Hale telescope on Palomar Mountain, and it landed on the desk of Maarten Schmidt. Schmidt was a Dutch astronomer, then in his early 30s, working at Caltech. He had the spectrum for weeks. He looked at it repeatedly. The lines were broad and bright and in the wrong places, and there were 6 of them, and nothing fitted. The account he gave afterwards is that on the 5th of February, 1963, he was writing up a short paper describing the spectrum as an unsolved curiosity, and he laid the plate out one more time and looked at the spacing of the lines rather than their absolute positions. The spacing was familiar. It was the hydrogen-Balmer series, the ladder of lines produced when electrons drop into the second energy level of a hydrogen atom, the most thoroughly documented pattern in all of spectroscopy, the thing every undergraduate learns to recognize. The whole ladder was intact. Every interval was in proportion. The pattern had simply been picked up and moved 16% toward the red, a redshift of 0.158. For a star, that is impossible. Stars in the Milky Way move at tens or a couple of hundred kilometers per second. A redshift of 16% would mean 47,000 kilometers per second, and nothing bound to this galaxy moves like that. But if the object was not in the Milky Way, if it was outside, far outside, carried along by the expansion of the universe, then the number was ordinary. It simply meant distance, about 2.5 billion light-years of it. Schmidt walked down the corridor. Greenstein was in his office. Within a short conversation, Greenstein had gone back to 3C48 and found that its unidentifiable lines were also familiar, shifted much further. a redshift of 0.367. Both papers went to Nature and were published together in the 16th of March issue, 1963. Schmidt's is 2 pages long. The immediate consequence was not excitement, it was alarm, because if 3C273 was 2.5 billion light-years away and still appeared as a 13th magnitude object, then it was radiating something like 100 times the total output of an entire large galaxy, and it was doing it from a region small enough to look like a point. Worse, these objects varied. Astronomers went back through the Photographic Archive's plate collections at Harvard and elsewhere, held images of the same patch of sky going back decades, and found that 3C273 had changed brightness substantially over periods of months. That constraint is severe, and it is worth being precise about why. If an object brightens across its whole surface in a month, then information about the brightening has to have crossed it in a month, and nothing crosses anything faster than light. So the object cannot be more than about a light month across. A light month, roughly 1,000 times the size of the solar system, and out of that volume, more light than 100 billion stars. No form of nuclear fusion can do this. Fusion converts about 0.7% of the rest mass of hydrogen into energy, and even at perfect efficiency, feeding an entire galaxy's worth of stars into a light month-wide box does not produce these numbers for long enough. The answer came from 2 people independently, in the same year, on opposite sides of the Iron Curtain. In 1964, Edwin Salpeter in the United States and Yakov Zeldovich in the Soviet Union each proposed that the power source was gravitational, matter falling onto a very massive, very compact object, converting its potential energy into heat and then into radiation on the way down. Salpeter went further and suggested the object was a supermassive black hole with a mass of millions or more solar masses at the center of a galaxy. The efficiency of that process is roughly 10% more than 10 times better than fusion, and unlike fusion, it does not require the fuel to be hydrogen. Anything works. Gas, dust, whole stars torn apart by tides. If you can get matter into the well pays out. The name arrived in 1964 from Hongyi Chu, writing in Physics Today. The full designation, quasi-stellar radio source, was unwieldy, and he shortened it, quasar. Within a few years, Donald Lyndon Bell drew the conclusion that made the whole picture uncomfortable and permanent. In a paper in 1969, he pointed out that if quasars burn out, and they clearly do, since they are far more common in the early universe than the late one, then their black holes do not go anywhere, they stay, which means the centers of ordinary, quiet, present-day galaxies should contain enormous dead black holes, the burnt-out remains of quasars that ran out of fuel billions of years ago, including ours. That prediction took 30 years to confirm and was eventually settled by watching individual stars whip around an invisible point at the center of the Milky Way. It was correct. So by the end of the 1960s, the framework existed. Point-like blue objects with impossible spectra were not stars. They were the nuclei of distant galaxies, powered by accretion onto supermassive black holes, visible across most of the observable universe because gravity is a more efficient engine than fusion. And in a bulletin in Puebla, in a list of faint blue objects nobody had revisited, entry number 618 was sitting there with the coordinates already written down. What connected the two was a radio telescope shaped like a cross, standing in a field of maize in the Po Valley. The Northern Cross at Medicina, near Bologna, does not look like a telescope. It looks like agricultural infrastructure. 2 arms laid out on the ground in the shape of a cross, an east-west arm consisting of a single cylindrical parabolic reflector well over 500 meters long, and a north-south arm made up of dozens of parallel cylinders. There is no dish, no dome, nothing that swivels dramatically. The structure barely moves. It does not need to. A transit instrument works by staying still and letting the Earth do the pointing. As the planet turns, the strip of sky the telescope is sensitive to sweeps westward, and over the course of a day, everything in that declination band passes through the beam. Adjust the phasing of the receivers and you shift the strip. Over months, you map the sky. The Northern Cross began operating in the 1960s, and when it was completed, It had one of the largest collecting areas of any radio telescope in the world. Its survey, the B2 survey, conducted at a frequency of 408 MHz, a wavelength of about 73 centimeters, eventually catalogued thousands of sources across the northern sky. The program was driven by Alessandro Braccesi at the University of Bologna. Braccesi was interested in exactly the question that mattered, not just where the radio sources were, but what they were. And the way to answer that was to take the radio list, take the optical catalogues of faint blue objects that already existed, and look for coincidences. This is unglamorous work, and it is how a great deal of astronomy actually gets done. You have a radio position with an error box a few arc minutes across. You go to the optical plates covering that patch of sky, and you look for anything unusual inside the box. Most of the time there is nothing, or there are several candidates and no way to choose. But sometimes there is a single faint blue object sitting inside the box, and the probability of that happening by chance is low enough to be interesting. Around 1970, a source in the B2 catalogue at 12 hours, 28 minutes, plus 30 degrees was matched to a faint blue stellar object from the Tonnantzintler list. The match meant something specific. Ordinary stars are not radio sources. A blue point of light that also emits at meter wavelengths is not a white dwarf, and it is not a hot subdwarf. By 1970, everybody in the field knew what that combination usually meant. TON 618 had become a candidate. There is an accident buried in that match, and it is worth naming, because TON 618 would very likely still be sitting unidentified in a Mexican catalogue without it. Most quasars are not radio sources. Roughly 1 in 10 produces strong radio emission. The rest are what astronomers call radio quiet, which does not mean silent but means faint enough at meter wavelengths that a survey like the one at Medicina would never have registered them. The division is real, and it is fairly sharp. The radio loud and radio quiet populations differ by a factor of hundreds in radio output, with relatively little in between, and after 60 years of work, there is still no complete explanation of what determines which side of the line a given quasar falls on. What produces the radio emission when it appears is a jet, somewhere very close to the black hole. Magnetic field lines threading the accretion flow become twisted by the rotation of the flow and, in the leading model, by the rotation of the black hole itself. Roger Blandford and Roman Znayak showed in 1977 that a spinning black hole embedded in a magnetic field can have rotational energy extracted from it electromagnetically, that the hole itself, not just the gas around it, can be made to do work. The result is 2 collimated beams of plasma fired out along the rotation axis at very nearly the speed of light, and the radio emission is produced by electrons spiraling in the magnetic fields of those beams. The jets of the largest radio galaxies extend for millions of light years, far beyond the visible extent of their host galaxies, and inflate enormous lobes of relativistic plasma in the intergalactic medium. So when the Northern Cross registered a source at that position, it was detecting something the optical plates could never have shown. Not the disk, not the clouds, but a magnetic structure anchored somewhere near the horizon, throwing material out of the galaxy entirely. And it was luck. If TON 618 had been one of the 9 in 10 quasars that do not do this, the radio survey would have found nothing at that position. The coincidence with the Tonnantzintler list would never have been noticed, and the object would have waited for one of the large optical surveys of the 1990s or later to pick it out of a color-selected catalogue. It would have been found eventually, but the entire chain that produced the number tonight, the plate, the radio match, the spectrum in Texas, the infrared measurement on Mauna Kea begins with the object happening to belong to a minority population for reasons nobody fully understands. What it needed now was a spectrum, and getting one was not trivial. 15th magnitude is faint for spectroscopy on a photographic plate. Spreading the light of a 15th magnitude point across a spectrum means each individual wavelength gets a very small share of a very small amount of light, and photographic emulsion is inefficient. A few % of arriving photons produce a chemical change, and the rest are simply wasted. Long exposures were the only option, which meant guiding a telescope by hand, or nearly by hand, for hours, keeping a nearly invisible object centered on a slit, a few arc seconds wide, while the dome rotated and the temperature dropped. The spectrum was obtained in 1976 at McDonald Observatory in the Davis Mountains of West Texas by Marie-Helene Ulrich. Ulrich is not a name that appears in the popular accounts of TON 618, and she should be. She was a French astronomer who spent much of the 1970s at McDonald and went on to a long career in active galactic nuclei, later at the European Southern Observatory. She worked on the spectra of these objects for decades, the shapes of their emission lines, the physics of the gas producing them, how the light varied over time. She was doing the unfashionable, careful, cumulative work that turns a class of objects from a curiosity into a subject. McDonald Observatory sits on Mount Locke, at just over 2,000 meters, in one of the darkest skies remaining in the continental United States. The telescope was almost certainly the 107-inch reflector, then relatively new, now named after Harlan Smith. It is a serious instrument, and in the mid-70s it was among the larger telescopes available to anyone outside California. The observation itself would have been unremarkable to watch. A dome open to cold desert air, a finding chart, the blue object acquired, centered, checked, the spectrograph slit closed down to cut sky background. Then an exposure lasting a substantial part of the night, with the observer at the guiding eyepiece, making small corrections, waiting. Afterwards, the darkroom, the developer, the fix, the wash, and then a plate held up against a light, with a thin band of exposed emulsion on it, and features visible in that band. The lines were broad and they were bright, and they were at wavelengths that, if you assumed they were the standard emission lines of a quasar, implied a redshift of 2.219. That number was, in 1976, a large one. That conversion, from a redshift to a time and a distance, is worth opening up, because it is not a lookup and it carries assumptions of its own into everything downstream. A redshift is a directly measured quantity. You identify a line, you compare where it arrived with where it is emitted in a laboratory. You take the ratio. 2.219 is about as solid a number as observational astronomy produces. There is essentially no argument about it. Turning that into a distance is a different matter entirely, because it requires knowing the entire expansion history of the universe between then and now. The light did not travel through a static space of fixed size. It traveled through a space that was expanding the whole way at a rate that changed. In the early part of the journey, the expansion was decelerating because the gravitational attraction of all the matter in the universe was pulling against it. Then, somewhere around 5 or 6 billion years ago, dark energy became the dominant term, and the expansion began to accelerate instead. So to convert a redshift into a look-back time, you need 3 things: the present expansion rate, the mean density of matter, and the density of dark energy. Feed those into the equations and integrate backwards. The standard values give 10.8 billion years for a redshift of 2.219 in a universe 13.8 billion years old. But the present expansion rate, the Hubble constant, is currently the subject of the sharpest unresolved disagreement in cosmology. There are 2 broad ways of measuring it. One works outward from the nearby universe, measure distances to relatively close objects by methods that do not depend on the cosmological model, build a ladder of overlapping techniques, and read the expansion rate off directly. That approach gives a value of roughly 73 kilometers per second per megaparsec. The other works from the cosmic microwave background, measure the pattern of temperature fluctuations in the radiation left over from the early universe, fit the cosmological model to it, and infer what the expansion rate must be today. That approach gives roughly 67. Those 2 numbers do not agree, and the gap is not shrinking as the measurements improve. It has been getting harder to explain, not easier, for over a decade. Both camps have been through their systematics repeatedly. This is what is called the Hubble tension, and at present nobody knows whether it is a subtle measurement problem in one of the 2 approaches or a sign that the standard cosmological model is incomplete. A gap of that size shifts the age of the universe and the inferred distance to everything in it by several percent. Several percent does not matter much for the mass of TON 618, and I want to be honest about that rather than inflate it. The dominant uncertainties in that number are the geometry factor and the extrapolated calibration, and those are worth a factor of 2.5 between them. A few percent of distance uncertainty is lost in the noise. But it is worth noticing where it enters, because it is the same pattern one level down. The distance sets the luminosity. The luminosity, through the radius-luminosity relation, sets the broad line region radius. The radius, with the velocity, sets the mass. Every number in this chain rests on a number below it, and each of those rests on something else. And at the bottom are quantities that are still being argued about by people with excellent instruments. Nothing here is a reading off a dial. It is inference all the way down, and the fact that it works at all, that the answers from independent chains generally agree to within a factor of a few, is the actual achievement. Redshifts above 2 were not every day. The quasar population known at the time thinned out considerably at the high end, and each new object up there was worth having. What the redshift meant, once folded through the cosmology, was that the light had been in flight for about 10.8 billion years, and that it had left when the universe was 2.9 billion years old. It also meant that the object's apparent brightness translated into an absolute output that put it near the top of everything then known. TON 618 was not merely a quasar, it was one of the most luminous objects in the observable universe. Before we leave that plate in Texas, I want to open the spectrum up, because a quasar spectrum is one of the densest single objects in observational astronomy, and almost nothing written for a general audience ever says what is in one. Start with what Ulrich would actually have seen. At a redshift of 2.219, every wavelength is stretched by a factor of 3.2. That does something useful. It takes the ultraviolet part of the quasar's spectrum, which is normally blocked entirely by the Earth's atmosphere and unavailable from the ground, and slides it down into the visible band where a photographic plate can record it. So the strongest feature in that Texas spectrum was almost certainly Lyman alpha, the fundamental transition of hydrogen, an electron dropping into the very lowest energy level, emitted at 1,216 angstroms in the far ultraviolet. Stretched by 3.2, it arrives at around 3,900 angstroms at the violet end of what the eye can just perceive. Next to it, the carbon line astronomers call C4, produced by carbon atoms stripped of 3 of their electrons, emitted at 1,549 angstroms and arriving at around 5,000, green. Then a second carbon feature further along, arriving in the orange, and a magnesium line, from magnesium missing 1 electron, emitted at 2,800 angstroms, and arriving right at the far red edge of the plate's sensitivity. 4 lines, all of them from the deep ultraviolet, all of them delivered into the visible by the expansion of the universe. Without the redshift, none of them would be observable at all from the ground. The distance that makes the object faint is the same thing that makes its spectrum readable. Now, the shapes. These lines are not all the same width, and the difference is structural rather than incidental. Some are enormously broad, hundreds of angstroms wide in the observed frame, smeared out by orbital motion of thousands of kilometers per second. Those come from the broad line region, deep in the black hole's gravity, the gas we discussed earlier. Others, in quasars generally, are narrow a few hundred kilometers per second at most. Those come from a completely different structure, hundreds or thousands of light years out, far beyond the black hole's dominant influence, where the gas is moving at ordinary galactic speeds. It is called the narrow line region, and it is essentially the quasar's light escaping in a cone and illuminating the surrounding galaxy from within. So, a single spectrum contains 2 separate measurements at 2 wildly different scales: the motion of gas a few light months from the horizon, and the motion of gas out in the galaxy. Reading the widths is reading a map, then the chemistry, which is where this gets genuinely strange. The carbon and magnesium lines should not be there. Carbon does not exist in the early universe, nor does magnesium or silicon or iron. The Big Bang produced hydrogen, helium, and a trace of lithium, and that is the entire inventory. Every atom heavier than that has been manufactured in the interior of a star or in the collision of stellar remnants, and released when the star died. So the presence of strong carbon and magnesium emission in the gas around a black hole, at a moment when the universe was 2.9 billion years old, means that a very large amount of stellar processing had already happened in that galaxy. Stars had formed, lived and died enough of them, and fast enough, to enrich the gas at the very center of the system. And it goes further than mere presence. When astronomers measure the abundances in the broad line regions of quasars at high redshift, they consistently find not just enriched gas, but heavily enriched gas several times. The abundance of heavy elements found in the Sun, which formed 9 billion years later out of material that had been accumulating enrichment the entire time. The gas around these early black holes is chemically older than the Sunday. That is the actual subject of the Schema paper. It was not a paper about the size of Ton 618. It was a study of the relationship between the chemical enrichment of quasar broad-line regions and how fast their black holes were accreting across a sample of luminous high-redshift objects. The mass estimate was a necessary ingredient. You cannot compute an accretion rate relative to the Eddington limit without a mass, and TON 618's mass appeared in a table because it had to, in service of a different question entirely. The most quoted number about this object was a byproduct. There is more in the spectrum, and some of it is not from the quasar at all. Blueward of Lyman alpha, the spectra of distant quasars are chewed up by a dense thicket of narrow absorption lines. They are called the Lyman alpha forest, and they are one of the most useful accidents in cosmology. Here is what produces them. Between us and Ton 618, there are 10.8 billion years of intergalactic space, and that space is not empty. It contains a diffuse web of hydrogen filaments and sheets of gas, the scaffolding along which galaxies formed. Every time the quasar's light passes through one of those clouds, hydrogen atoms in the cloud absorb at exactly Lyman alpha, removing a narrow slice of the beam. But the cloud has its own redshift, depending on how far away it is, so the slice is removed at a slightly different observed wavelength for every cloud. The result is a comb of absorption lines, dozens or hundreds of them, each one recording a separate cloud of gas at a separate distance along a line of sight, 10 billion light-years long. The spectrum is not just a measurement of the quasar, it is a core sample through the universe. That is what quasars are used for now, more than anything else. They are the only sources bright enough and distant enough to backlight the intergalactic medium, and the forest of absorption in their spectra is how we have mapped the distribution of ordinary matter between galaxies across cosmic time. Ton 618, whatever its mass turns out to be, is a lamp behind 10 billion years of gas. And there is one more feature, which shows up in a minority of quasars and matters for how much we should trust the mass. Some quasars, roughly 1 in 5, show broad absorption lines, deep troughs carved into the blue side of their emission lines, indicating gas moving toward us at extraordinary speed, not orbiting, leaving. In the most extreme cases, these outflows are traveling at 10 or 20% of the speed of light, driven outward by radiation pressure from the disk. That is a direct observation that the gas around these black holes is not purely under the control of gravity. Radiation is pushing it. And if radiation pressure contributes meaningfully to the motion of the broad-line clouds specifically, then the line width we measure is not purely orbital. The virial assumption is violated, and the mass comes out too high. This is not a hypothetical objection raised by skeptics. It is a known physical effect, observed directly in a substantial fraction of the population, and the degree to which it contaminates virial mass estimates in the most luminous quasars, which are exactly the ones with the strongest radiation fields, is an open question. So the spectrum contains the redshift, the distance, the luminosity, the composition of the gas, the depth of the gravitational well, the structure of the emitting regions, a map of the intergalactic medium along 10 billion light-years, and a warning about the reliability of the mass. What it does not contain is the mass itself. That is where the identification stopped. And it is worth being clear about why it stopped there, because the gap that opens here is the gap the rest of tonight is about. A spectrum tells you a great deal. It tells you the redshift, and therefore the distance, and therefore combined with the apparent brightness, the intrinsic luminosity. It tells you which atoms are present and roughly what state they are in. It tells you, from the widths of the lines, how fast the emitting gas is moving. What it does not tell you is mass. Luminosity is not mass. Brightness measures how hard the engine is running, not how big the engine is. A small black hole feeding at its absolute maximum, and a much larger one idling at a few percent, can produce the same output. Nothing in the spectrum, on its own, distinguishes them, and the black hole itself contributes exactly nothing to the light. The event horizon does not emit, it does not reflect, there is no surface. Everything we detect from TON 618 comes from gas that has not yet fallen in, and the object we actually want to measure sits behind that light, entirely dark, inferred rather than observed. So after 1976, the situation was this. We knew where it was. We knew how far away it was. We knew, to within reasonable error, how much energy it was pouring out. We knew the gas around its center was moving at thousands of kilometers per second, because the emission lines were smeared out by Doppler shift into broad humps rather than sharp spikes. We did not know how much matter was at the middle, and we had no method that could tell us. The width of a spectral line gives you a speed. Speed alone is useless. A cloud orbiting at 7,000 kilometers per second could be very close to a modest mass, or very far from an enormous one, and those two possibilities produce identical spectra. To break that ambiguity, you need to know how far the gas is from the center, and that gas sits at a distance so small, seen from 10.8 billion light-years away, that no telescope ever built or currently planned could resolve it. The mass of TON 618 was, in 1976, not merely unknown. It was inaccessible in principle, given the instruments and the ideas that existed. Closing that gap took another 28 years, and the solution, when it came, did not involve looking at TON 618 at all. It came from a long, tedious, deeply unfashionable campaign of watching much smaller and much nearer galaxies flicker. But before we can follow that, we need to understand what is actually producing the light, because the trick that eventually delivered the mass depends entirely on the structure of the thing and on one particular region of gas that nobody could see and everybody had to reason about. A star shines because it is fighting a losing battle with its own weight. Gravity pulls inward. Fusion in the core produces heat and pressure that push outward. The two balance for a while, and the light we see is what leaks out of the top of that argument. Every star is a slow, controlled failure, and when the fuel runs out, the failure completes. A quasar shines for the opposite reason. Nothing is holding anything up. The light is what gravity produces when it wins. Here is the mechanism. Gas in a galaxy is not at rest. It is orbiting, turbulent, threaded with magnetic fields, and above all, it has angular momentum, a parcel of gas somewhere in the inner region of a galaxy that begins to fall toward the center, cannot fall straight in, because it is already moving sideways. What it does instead is spiral. And because every parcel is doing this, and they are arriving from different directions with different amounts of sideways motion, they collide, they shock, they rub. Over time, and this is the crucial step, the collisions average everything out into a single plane, rotating in a single direction. A disk. Once the disk exists, friction becomes the engine. Material closer to the center orbits faster than material further out, so adjacent rings of gas slide past each other, and that shearing motion, mediated mostly by magnetic turbulence rather than ordinary viscosity, transfers angular momentum outward. Gas that loses angular momentum sinks. Gas that gains, it moves out. The net result is a slow inward drift, and every centimeter of that drift releases gravitational potential energy as heat. The mathematics of this was worked out in 1973 by Nikolai Shakura and Rashid Sunyaev in a paper that is still the standard reference. Their model is called the thin disk, and its central assumption is a fudge. They bundled all the unknown turbulent physics into a single parameter and got on with it. But the structure it predicts has held up remarkably well. What it predicts is this. The disk is geometrically thin and optically thick. A broad, flat sheet, much wider than it is deep, dense enough that radiation cannot escape directly from its interior but must work its way to the surface. The temperature rises steeply as you move inward, and the total energy released depends on how deep the gas gets before it disappears. That depth is set by a boundary called the innermost stable circular orbit. This is one of the genuinely strange consequences of general relativity, and it has no equivalent in Newton's universe. Around an ordinary object, there is no closest possible orbit. You can orbit at any radius you like, arbitrarily near the surface, and the orbit is stable. Around a black hole, this stops being true. Below a certain radius, orbits become unstable. Nudge the gas slightly, and instead of settling into a new orbit, it spirals rapidly inward and is gone. For a black hole that is not spinning, that boundary sits at 3 times the Schwarzschild radius. So the accretion disk has an inner edge, not a physical wall, just a radius below which orbiting is no longer a thing matter can do. Gas grinds inward through the disk, reaches that edge, and then falls, in a plunge that takes a fraction of the time everything before it took, and crosses the horizon. The efficiency of the whole process, the fraction of the infalling mass that comes out as light rather than disappearing, is set by how deep that inner edge sits. For a non-spinning black hole, it is about 6%. For a rapidly spinning one, where frame dragging pulls the innermost stable orbit much closer in, it can reach 30 or 40%. Nobody knows the spin of TON 618's black hole. The conventional assumption is around 10% efficiency, which is a reasonable middle. Compare that with the Sun, which, over its entire 10 billion year lifetime, will convert something like 0.7% of its available hydrogen mass into energy, and you can see why gravity beats fusion so decisively. Falling into a deep enough hole is more than 10 times better than burning. Now let us put the numbers of TON 618 into that structure, because the scale of the thing does something counterintuitive. The Schwarzschild radius is 1,300 astronomical units. The innermost stable orbit, therefore, sits at about 3,900 astronomical units, roughly 130 times the distance from the Sun to Neptune. That is the inner edge of the disk. The disk extends outward from there, probably by a factor of 10 or 20, which makes the luminous structure something on the order of tens of thousands of astronomical units across. If you placed it around the Sun, its outer regions would be well on the way to the nearest star. At that inner edge, the gas is moving at a substantial fraction of the speed of light for a non-spinning black hole, something around half, which means you can work out how long one lap takes. The circumference at 3,900 astronomical units is about 3.7 trillion kilometers. At half the speed of light, a parcel of gas completes that circuit in roughly 9 months. 9 months. A parcel of superheated plasma, moving at 150,000 kilometers per second, fast enough to cross the distance from the Earth to the Moon in under 3 seconds, takes most of a year to get once around the innermost orbit it can occupy. Compare that with the black hole at the center of our own galaxy, where the equivalent orbit takes about half an hour, and there is a second consequence of scale, which I find harder to shake than the first. The temperature of an accretion disk depends on how much mass is being crammed through how small an area. Bigger black holes have vastly bigger disks, so the same relative accretion rate is spread over far more surface, and the disk runs cooler. The relationship is not dramatic. Temperature falls off as roughly the fourth root of the mass, but across a factor of 10 billion in mass, it adds up. The accretion disk around a stellar mass black hole runs at millions of degrees and shines mostly in X-rays. The disk around TON 618 peaks at something in the region of a few tens of thousands of degrees, in the far ultraviolet, sliding down into the blue. That is why the plate in Mexico recorded it as a blue object. The single defining characteristic that got it into a catalogue in the first place, its blueness, is a direct consequence of its mass. The largest black hole ever weighed made itself known to humanity by producing a disk slightly too cool to be a hot star and slightly too blue to be anything else, and by looking, on a photographic negative, marginally wrong. Let me place you inside this for a moment, because the geometry is worth inhabiting rather than only reading. You are somewhere well outside the system, far enough that the whole structure fits in your field of view. There is no roar, no wind, nothing to hear. What you see is a broad, flat disk, brilliant white blue toward the center and fading through violet to darkness at its rim, lying across a distance that would take light most of a day to cross. Toward the middle, the brightness climbs steeply, and then, at a certain radius, it stops. Not faders, stops. There is a circular region at the center from which nothing comes, and around its edge the light is bent. You can see parts of the far side of the disk lifted into view, above and below the dark circle, because the light from behind is being curved over the top of the hole and delivered to your eye. Nothing about the dark region is a surface. There is nothing there. It is the set of points from which no path leads back out, and it is defined entirely by geometry. And the whole structure is barely moving as far as you can tell. You would have to watch for weeks to see the inner disk turn measurably. It is the least dramatic thing imaginable, an enormous, patient, silent wheel. Now, the limit. There is a maximum brightness for any object that shines by accretion, and the argument that establishes it is one of the more elegant pieces of reasoning in astrophysics. It was worked out by Arthur Eddington in the 1920s. For stars, long before anybody was thinking about black holes, light carries momentum. When radiation streams outward through ionized gas, it collides with free electrons and pushes on them. The electrons are electrically bound to the protons around them, so they drag the protons along too. The result is an outward force on the gas, proportional to the luminosity. Meanwhile, gravity pulls the same gas inward, with a force proportional to the mass. Both forces fall off as the square of the distance, which means their ratio is the same everywhere. So there is a single luminosity at which the outward push exactly cancels the inward pull, and it depends only on the mass of the central object. Below it, gas can fall in. Above it, radiation blows the fuel supply away, and the accretion chokes itself off. That is the Eddington limit, and here is where it puts TON 618. For 66 billion solar masses, the Eddington luminosity is about 8 times 10 to the 48th ergs per second. The observed luminosity is 4 times 10 to the 47th. The ratio is about 1 in 20, 5%. Take the mass estimate down to its lower bound, and the figure rises toward 15%, but it does not approach the ceiling under any reading of the data. I want to give that a moment, because it inverts the story that usually gets told about this object. The most massive black hole we have ever measured is not devouring. It is not straining at its limit, not tearing its surroundings apart, not consuming at the outer edge of what physics allows. It is eating 70 suns a year in a galaxy that presumably contains hundreds of billions of them, which at that rate would take longer than the current age of the universe to work through a single % of the available material. It is producing 140 trillion solar luminosities while operating at 1/20th throttle. The violence is entirely a function of size. Nothing about the process is frantic. It is just very, very large. 2 more components, and then the structure is complete. The disk alone cannot account for everything we detect. Quasars emit X-rays, and a thin disk at a few tens of thousands of degrees cannot produce them. You need matter at temperatures of 1 billion degrees or more, and there is nothing in the disk model that gets there. What produces them is a corona, a region of extremely hot, very thin plasma sitting above and below the inner disk, in much the same geometric relationship as the sun's corona sits above its visible surface, and about as poorly understood. Electrons in that plasma are moving at relativistic speeds. When an ultraviolet photon from the disk passes through, it collides with one of them and is kicked up in energy, a process called inverse Compton scattering, where the photon takes energy from the electron rather than giving it up. A photon that entered the corona as ultraviolet leaves it as an X-ray. We know the corona is compact, because its X-ray output varies faster than anything else in the system. Rapid variability means small size by the same light travel argument that constrained the size of 3C273 back in 1963. The corona appears to occupy a region only a few times the size of the event horizon. There is a relationship here that bears directly on our number, and it is one Schemmer himself worked on. The ratio of X-ray output to ultraviolet output in quasars is not constant. It declines systematically with luminosity. The brightest quasars produce proportionally fewer X-rays than modest ones. Nobody has a settled explanation. It may be that at very high accretion rates the disk puffs up and shields the corona, or that the corona itself is disrupted, or that photons are being trapped in the flow before they can be scattered. Whatever the cause, TON 618 sits at the extreme end of that relation too. It is, relative to its enormous optical and ultraviolet output, X-ray faint. The second component is not a structure, but a limit, and it explains where the disk stops. An accretion disk is held in shape by the gravity of the central black hole, but the disk has mass of its own, and as you move outward, the black hole's pull weakens while the amount of disk material enclosed grows. At some radius, the disk's own self-gravity becomes comparable to the central object's grip on it. Past that radius, the disk becomes unstable. Small overdensities collapse under their own weight rather than being sheared apart, and the disk fragments not into a smooth flow, but into clumps, which contract, and which then do what dense clumps of gas always do. They form stars. So the outer edge of an accretion disk is not a boundary where material runs out. It is a boundary where the material stops being a disk and starts being a star-forming region. Beyond it, the gas that might have fed the black hole is converted into objects that orbit it instead, and orbit for billions of years and never fall in. That is not a footnote. It is the leading explanation for why black holes cannot grow indefinitely. The bigger the black hole, the bigger the disk, and the more of the incoming fuel gets intercepted and turned into stars before it can reach the center. Eventually, the fraction that gets through drops so low that growth effectively stops, regardless of how much gas the galaxy has. Which is why the theoretical ceiling on black hole mass sits where it does, and why the objects at the top of the list, including this one, are all clustered near it rather than spread out above it, which leaves one more component, and it is the one that matters for everything that follows. Outside the disk, but still deep inside the region dominated by the black hole's gravity, there is gas that is not in a disk at all. It exists in discrete clouds, dense, fast-moving, filling a volume rather than a plane, and probably being blown around by radiation, as well as pulled by gravity. This is the broad-line region. These clouds do not generate their own light. They are illuminated. The intense ultraviolet and X-ray continuum from the inner disk floods outward and strikes them, and the photons are energetic enough to strip electrons from atoms. The atoms then recombine electrons, falling back down through the available energy levels, and each drop emits a photon at a precisely determined wavelength. That is what an emission line is, not a glow, but a specific quantum transition happening in enormous numbers. Hydrogen dominates, as it dominates everything in the universe by number. The line we care about most is called H-beta, produced when an electron falls to the second energy level from the fourth, and in a laboratory on Earth, it sits at 4,861 angstroms, a clean blue-green. In the spectrum of TON 618, that line is not clean and it is not a spike. It is an enormous smeared hump, with a full width at half its peak height corresponding to about 7,000 kilometers per second. That width is not an accident of the instrument. It is the clouds themselves. They are in orbit. Some are on the far side, moving away, and their light is redshifted a little further. Some are on the near side, coming toward us, and their light is shifted back toward the blue. Some are moving across our line of sight and contribute nothing. Add together the emission from millions of clouds at every orientation, and the sharp laboratory line becomes a broad profile whose width encodes the typical orbital speed, 7,000 kilometers per second. For comparison, the Earth orbits the Sun at 30. The Sun orbits the center of the galaxy at about 220. These clouds are moving at more than 2% of the speed of light. And orbital speed is set by gravity, which means it is set by mass. There is the opening. If you know how fast something orbits, and you know how far out it is orbiting, then you know the mass inside its orbit. That is not a subtle relationship or a statistical correlation. It is the oldest result in celestial mechanics, the thing Newton wrote down, and it works identically for a moon around a planet and a cloud of hydrogen around a black hole 10 billion light-years away. The width of the line gives the speed. The speed is measured directly from a single spectrum. Everything, therefore, depends on the other quantity. How far out are the clouds? And that, for a quasar at redshift 2.2, is a question with no observational answer. The entire broadline region of TON 618, seen from Earth, subtends an angle of a few millionths of an arcsecond. The Hubble Space Telescope resolves about a tenth of an arcsecond. You would need an instrument roughly 100,000 times sharper. Nothing on any drawing board approaches it. We cannot photograph these clouds, cannot separate them from the disk, cannot trace a single orbit. So the radius has to be obtained some other way entirely, and the method that eventually delivered it works by ignoring the geometry altogether and paying attention to time. The idea is called reverberation mapping, and it was proposed in 1982 by Roger Blandford and Christopher McKee. Start from an observation that had been irritating astronomers for years. Quasars flicker. The continuum light from the inner accretion disk is not steady. It rises and falls by a few percent over weeks and months in a way that is essentially unpredictable, presumably because the accretion flow is turbulent and lumpy rather than smooth. Now think about what that variability does to the clouds. The broad line region is lit entirely by the central continuum. If the continuum brightens, the clouds receive more ionizing photons and respond by emitting more line radiation. They brighten too, but not immediately. The light announcing the change has to travel from the disk out to the clouds, and light has a finite speed. So the emission lines follow the continuum with a delay. And the delay is the light travel time from the center to the clouds. Measure the delay in days, and you have the radius in light days. That is the entire concept, and it is beautiful because it converts a spatial measurement that is impossible into a timing measurement that is merely very difficult. Very difficult is not an overstatement. To detect the lag, you must monitor both the continuum brightness and the emission line strength of the same object, repeatedly, with a cadence of a few days, for months on end. You need photometric accuracy good enough to see a few percent of variation. You need the weather to cooperate over an entire season. You need the same instrument or carefully cross-calibrated instruments so that changes in the data are changes in the object rather than changes in your equipment. And you need to do it for object after object, across a range of luminosities, before you can say anything general. This is not the kind of program that produces a result in a year. It is the kind that consumes a decade. The person who made it work was Bradley Peterson at Ohio State University. Peterson spent much of the late 1980s and the 1990s organizing international monitoring campaigns on a handful of nearby active galaxies, Seyfert galaxies, named after Karl Schwarzschild, who catalogued the first examples in the 1940s. Seyferts are the modest relatives of quasars, the same physics, black holes of a few million to a few hundred million solar masses, accreting steadily, embedded in galaxies whose stars you can still see. They are nearby and comparatively faint, which makes them possible to observe on small telescopes and impossible to observe quickly. The campaigns ran under the banner of an international monitoring collaboration, and they were exercises in logistics as much as astronomy. Dozens of astronomers at telescopes in Arizona, Chile, South Africa, Australia, and elsewhere coordinated their schedules so that a target galaxy was observed on as many clear nights as possible, from as many longitudes as possible, and the resulting spectra were shipped, calibrated, cross-checked, and assembled into a single continuous record. The flagship target was a Seyfert galaxy catalogued as NGC 5548. It has now been monitored, on and off, for more than 3 decades, one of the longest continuous observational records of any object in extragalactic astronomy. It is worth saying how much labor is buried in that single sentence about calibration, because the phrase, "the relation was calibrated," conceals decades of the least glamorous work in the field. A reverberation campaign is not an observation, it is a season. It means booking telescope time not for a night or two, but for dozens of nights spread across months, at multiple observatories, with the understanding that a substantial fraction will be lost to weather, and that a gap of 2 weeks in the middle can render the entire lag measurement ambiguous. It means calibrating spectra taken with different instruments, under different conditions, by different people, to a consistency of a few percent, because the signal you are looking for is a few percent. It means arguing about how to remove the contribution of the host galaxy's starlight, which sits underneath the quasar's continuum and does not vary, and which, if mishandled, biases everything downstream. And it means doing all of that for objects that produce, at the end, a single number, a lag, in days, with an error bar. The program has continued and intensified. In 2014, an exceptionally intensive campaign pointed the Hubble Space Telescope at the same Seyfert galaxy that anchored the original work. For over 100 orbits across 6 months, supported by ground-based observatories on several continents and by space telescopes observing in X-rays and ultraviolet simultaneously. It is one of the most intensive monitoring campaigns ever conducted on a single extragalactic object. It also produced an anomaly that nobody has fully explained. Partway through, the emission lines stopped tracking the continuum. The central source went on varying. The broad line region simply failed to respond in the expected way for a period of weeks before resuming. The effect was promptly nicknamed the holiday, which is the kind of name a field gives something when it has no idea what caused it. That anomaly matters here. The single epoch method that produced the mass of TON 618 assumes the broadline region responds to the continuum in a simple, stable, geometrically well-behaved way. The best observed broadline region in the universe demonstrably does not always do that. The result was clean. The continuum varied. The H-beta line followed it, with a lag of about 20 days. 20 light days. Around 3,500 astronomical units. The broad line region of that galaxy turned out to be a structure roughly the scale of a very large solar system, sitting around a black hole of a few tens of millions of solar masses, and now, finally, measured. Do that for one object, and you have one number. Do it for dozens, across a range of luminosities, and a pattern emerges, and the pattern is what made everything else possible. More luminous nuclei have larger broad line regions. The relationship is close to a square root law. Quadruple the luminosity and the radius doubles. The physics behind that is straightforward once you see it. The clouds exist where the radiation field has the right intensity to produce the ions in question too close, and the gas is stripped bare, too far, and it stays neutral. If the central source is brighter, that sweet spot moves outward. And because light spreads out as the square of distance, the radius scales as the square root of the luminosity. It is not an empirical curiosity. It is what photoionization requires. That relationship, the radius-luminosity relation, was pinned down through the late 1990s and the 2000s by Peterson and by Shai Caspi, Misty Bentz, and others, and it is the hinge on which the entire mass scale of distant black holes turns. Because it means you no longer need years of monitoring. You need one spectrum. From a single spectrum, you measure two things: the width of the H-beta line, which gives you the orbital speed of the clouds, and the brightness of the continuum, which via the radius-luminosity relation gives you the radius. Multiply the radius by the square of the velocity, divide by Newton's gravitational constant, and out comes a mass. That is the single epoch virial method. It is the workhorse of the field. It is how the masses of hundreds of thousands of quasars have been estimated. And it is how the number 66 billion came to exist. There is one term in that equation I have not mentioned, and it is where the trouble lives. The relationship between orbital motion and enclosed mass depends on the geometry of the orbits. If the clouds form a spherical swarm moving in random directions, the observed line width relates to the true orbital speed one way. If they form a flattened, disk-like distribution, it relates a different way, and critically, in that case, the answer depends on the angle at which we happen to be viewing the system. A disk of clouds, seen edge-on, shows the full orbital velocity as line-of-sight motion. The same disk seen face-on shows almost none, because everything is moving across our view rather than toward and away. So the equation carries a correction factor, universally written as f, which absorbs all of that unknown geometry into a single number. Estimates of f in the literature range from about 1 to about 5.5, depending on the calibration used and the assumed structure. A factor of 5, in a term that multiplies the answer directly. Nobody has ever measured the geometry of a broad line region directly. The value of f in general use is obtained by assuming that black holes in active galaxies obey the same relationship between mass and host galaxy properties as black holes in quiet galaxies, and then choosing whatever value of f makes the two agree on average. That is a defensible procedure. It is also, unmistakably, a calibration against an assumption rather than a measurement. By the early 2000s, all the pieces existed. The relation had been calibrated on roughly 36 active galaxies, almost all of them Seyferts and low-luminosity quasars, with black holes ranging from a few million to a few hundred million solar masses. TON 618 is not in that range. TON 618 is 1,000 to 10,000 times more luminous than the objects the relation was built from. Applying it anyway meant extrapolating far beyond the calibrated region, on the assumption that the same physics scales up unchanged. The astronomers who did it knew that. They said so. In 2004, a group led by Ohad Shemer, then at Tel Aviv University, set out to measure the black hole masses of the most luminous quasars known, and TON 618 was on the list. The observational problem was specific and awkward. The mass measurement depends on h-beta, because h-beta is the line the entire reverberation calibration was built on. H-beta sits in the blue-green at 4,861 angstroms, but TON 618's light is redshifted by a factor of 3.2. That line does not arrive here as blue-green. It arrives at around 15,600 angstroms, 1.5 microns, well into the infrared, invisible to conventional optical detectors, and sitting in a part of the spectrum where the Earth's own atmosphere, full of water vapor, glows and absorbs. To measure it, you need an infrared spectrograph on a very large telescope at a site high and dry enough that the atmosphere above it is thin on water. They used one of the twin 10-meter telescopes of the Keck Observatory on the summit of Mauna Kea at 4,200 meters. At that altitude, roughly 40% of the atmosphere is below you, and most of the water vapor is far below, frozen out. It was, and largely remains, one of the small number of places on Earth where that observation is possible at the required sensitivity. The instrument was a near-infrared spectrograph, cooled to cryogenic temperatures so that its own thermal glow would not swamp the signal. The spectrum came back showing H-beta clearly, a broad, roughly symmetric hump sitting on the bright continuum of the quasar. Its width at half maximum measured about 7,000 kilometers per second. Feed that width and the continuum luminosity through the radius-luminosity relation and the virial formula, and the answer comes out at 6.6 times 10 to the 10th solar masses, 66 billion. It was the largest black hole mass ever derived by that method, roughly double the previous highest, and it landed in a paper that was, in every respect that matters, careful. It did not claim a record. It did not claim to have found the largest black hole in the universe. It reported a number in a table, alongside numbers for other quasars, with an uncertainty attached, and a discussion of where that uncertainty came from. The uncertainty was about a factor of 2.5 in either direction, which is to say, somewhere between 20 billion and 200 billion solar masses, with 66 billion as the central estimate. And those errors are not the kind that go away if you observe longer. They are systematic. The radius-luminosity relation is being stretched 1,000-fold beyond its calibration. The geometry factor is unknown to a factor of 5. The clouds may be pushed outward by radiation pressure as well as held by gravity, in which case their speed is not purely orbital and the mass is overestimated. The viewing angle is unknown, and if we happen to be looking at a flattened cloud distribution close to face-on, the true orbital speed is higher than the line width suggests, and the mass is underestimated. Take 1,000 more spectra of TON 618 and every one of those problems remains exactly where it was. That is the machine that produced the number. Now we can ask what the number actually builds. There is a formula that turns a mass into a size, and it is short enough to hold in your head. The radius of a black hole's event horizon equals twice the gravitational constant times the mass, divided by the speed of light squared. Everything except the mass in that expression is a fixed property of the universe, which means the formula is a straight line. Double the mass, double the radius. There is no curve, no threshold, no complication. A black hole's size is simply its mass, in different units. For one solar mass, the answer is 3 kilometers. Take the Sun 1.5 million kilometers across, 1 million Earths by volume, and compress it until it is a sphere 6 kilometers wide, and it becomes a black hole. That is the whole condition. Not destroyed, not annihilated, just packed in past a certain density, after which the collapse continues on its own, and nothing can arrest it. For the Earth, the answer is about 9 millimeters. Our planet, crushed to the size of a marble. For the 4 million solar masses at the center of our galaxy, 12 million kilometers, about a fifth of the distance from the Sun to Mercury, comfortably inside the orbit of any planet. For the 6.5 billion solar masses of M87, about 120 astronomical units, that is a shadow that would sit entirely inside the Kuiper belt. And that shadow, at 55 million light-years, is what a planet-wide array of radio telescopes was built to resolve, and it took years of work to produce an image of a fuzzy ring. For 66 billion solar masses, the answer is 1,300 astronomical units. Let me set that down carefully, once, and then leave it standing. Place the black hole where the Sun is. The horizon is not a surface, and there is nothing to see, so what happens is simply that the sky stops. From any point inside that boundary, there is no path out, not for a spacecraft, not for a radio signal, not for light. Mercury is inside, at 4/10 of an astronomical unit, Venus at 7/10, the Earth at 1, Mars at 1.5, the asteroid belt entire, Jupiter at 5, with its 90-odd moons and its storm that has been running for centuries, Saturn at 9.5, with its rings which are themselves a structure 280,000 kilometers wide and, at most, tens of meters thick, one of the most delicate large objects in the solar system, Uranus at 19, Neptune at 30. At 30 astronomical units, we have reached the edge of what most people mean by the solar system, and we have covered slightly more than 2% of the distance to the horizon. Beyond Neptune, the Kuiper belt, from 30 out to about 50, containing Pluto and Eris and Makemake and Haumea, and hundreds of thousands of smaller icy bodies inside. The scattered disk beyond that, out to a few hundred astronomical units, where objects on long, eccentric orbits spend most of their time. Inside, at around 120 astronomical units, the heliopause, the boundary where the solar wind finally loses its argument with the interstellar medium and the Sun's influence, in the practical sense, ends. Inside, the horizon is still nearly 11 times further out. At 1,300 astronomical units, we are in the region where the innermost members of the Oort cloud are thought to begin the vast, roughly spherical reservoir of cometary nuclei that surrounds the solar system, holding perhaps 1 trillion objects, each on an orbit taking tens or hundreds of thousands of years to complete. The horizon reaches into the near edge of that shell and stops. Everything I have just listed, every planet, every moon, every ring, every comet in the inner reservoir, every spacecraft humanity has ever launched, every signal we have ever transmitted into the sky would be inside, and none of it would ever be heard from again. Now the second measure, which is time. Light takes 8 minutes and 20 seconds to reach us from the Sunday. It takes about 4 hours to reach Neptune. It takes roughly 20 hours to reach the heliopause. To cross from the center of TON 618's horizon to its edge, light needs 7.5 days. To cross the full width of the shadow, 15 days. 2 weeks at 300,000 kilometers per second. There is one object that makes this properly concrete, because it is real and it is ours. Voyager 1 launched in September of 1977. It has been in flight for nearly 50 years. It has passed Jupiter and Saturn, been flung out of the plane of the planets, crossed the heliopause into interstellar space, and it is currently about 170 astronomical units from the Sun, receding at roughly 17 kilometers per second. It is the most distant object human beings have ever made, and its radio signal, transmitted with about the power of a refrigerator bulb, still arrives. It has covered around 13% of the distance to this event horizon. If Voyager 1 were flying outward from the center of TON 618's black hole, it would have another 3 centuries of travel before it reached the boundary, and when it crossed, nothing would happen. There would be no shudder, no flash, no threshold to feel. That is the part people get wrong most often, and it is worth being clear about. For a small black hole, the approach is violent. Tidal force is the difference in gravitational pull across an object, and near a stellar mass black hole that difference is enormous. Over a distance of a few meters, your feet would be pulled far harder than your head, and you would be drawn out into a thread long before you reach the horizon. Tidal force falls off with the cube of the radius. Multiply the radius by 10 billion, and the tidal effect across a human body becomes so small it is below any threshold of sensation. At the horizon of TON 618, you would notice nothing at all. No warning. The stars behind you would still be visible. The disk would still be blazing somewhere in your view. Your instruments would read normally. The only thing that would have changed is that every possible future path now leads inward. Not most, all. The horizon is not a place where something is done to you. It is a place after which every direction you can point is the same direction. The name attached to that boundary belongs to a man who never learned that it described anything real. Karl Schwarzschild was born in Frankfurt in 1873 into a large Jewish family with a printing business and no particular scientific tradition. He was a prodigy in the most literal sense. He published 2 papers on the orbits of binary stars before he was 17. He went on to Munich and then to a chair at Göttingen, working alongside David Hilbert and Hermann Minkowski, and by 1909 he was director of the Astrophysical Observatory at Potsdam, one of the most senior positions in German astronomy. His work up to that point was broad and practical. He did fundamental work on photographic photometry, establishing how the density of an image on a plate relates to the light that produced it, which is the theoretical basis for exactly the kind of survey work being done at Tonant-Sintler 40 years later. He worked on radiative transfer in stellar atmospheres. He was, by any measure, one of the leading physical scientists in Europe. When the war began in 1914, he was 41 years old, married, with 3 children, and holding a position that made military service entirely unnecessary. He volunteered anyway. He served first in Belgium, then in France, then on the Eastern Front, where he was commissioned as an artillery officer. His duties involved calculating shell trajectories, ballistics, which is applied mechanics, and which he was almost certainly the most overqualified man in Europe to be doing. In November of 1915, Einstein presented the completed field equations of general relativity to the Prussian Academy. The theory replaced gravity as a force with gravity as geometry. Mass and energy curve, space-time, and objects move along the straightest available paths through that curvature. The equations were 10-coupled, non-linear partial differential equations, and Einstein did not expect exact solutions to be found. He had obtained his own predictions by approximation. Schwarzschild, in a dugout on the Russian front, got hold of the paper. Within weeks he had produced an exact solution, the complete description of the spacetime outside a spherical, non-rotating mass. He sent it to Einstein in a letter dated the 22nd of December, 1915, roughly a month after the theory had been published. Einstein's reply is well documented, and the surprise in it is real. He had not expected anyone to find an exact solution to the problem so simply, and he presented the paper to the Academy on Schwarzschild's behalf in January. A month later, Schwarzschild sent a second paper describing the interior solution for a sphere of fluid. Inside the mathematics was something that looked like a flaw. At a particular radius, the one that now bears his name, the equations misbehaved. Terms went to 0 and infinity. The coordinate system fell apart. For decades, this was treated as a mathematical artifact of no physical relevance, and in a sense that was right. It is a coordinate singularity, not a physical one, and an observer falling through it would find nothing there. But it took until the 1930s and 40s for the physics to be understood, until the 1960s for the term black hole to be coined, and until the 1970s for the astronomical community to accept that such things actually exist. Schwarzschild saw none of it. On the front, he contracted pemphigus, an autoimmune disease in which the immune system attacks the proteins binding skin cells together, causing severe and spreading blistering. In 1916, there was no treatment. He was invalided home in March, and he died on the 11th of May, at the age of 42, less than 5 months after posting the solution. His son Maarten, then 4 years old, became one of the 20th century's major astrophysicists and did foundational work on how stars evolve and die, including the processes that produce the collapsed objects his father's equations had described. The last thing to say about the scale is that it is not fixed, because the mass is not fixed. Everything I have just laid out, the swallowed planets, the 7.5 light days, the 3 centuries of Voyager travel, follows from taking 66 billion at face value. The formula is exact. The input is not. At the lower bound of the uncertainty, 20 billion solar masses, the horizon radius drops to about 400 astronomical units. That still swallows the entire planetary system and the Kuiper belt with room to spare, but it no longer reaches anywhere near the Oort cloud, and light crosses it in under 5 days instead of 15. At the upper bound, 200 billion, the radius is roughly 4,000 astronomical units. That is deep into the Oort cloud, a shadow that light needs over a month to traverse, and a volume 1,000 times larger than the lower bound version. So the honest description of the physical size of this object is not a number. It is a range, spanning a factor of 10 in radius and a factor of 1,000 in volume, and the range exists entirely because of the geometry factor and the extrapolated calibration we discussed earlier. The shadow is exactly as uncertain as the arithmetic that produced it. Since we have twice now compared this object with M87, it is worth asking directly whether TON 618 could ever be imaged the way that one was, because the answer is more interesting than a flat no. The relevant quantity is angular size, how large the shadow appears on the sky, which depends on its physical size divided by its distance. The shadow of M87's black hole subtends about 40 microarcseconds. A microarcsecond is a millionth of one arcsecond, and an arcsecond is 1/3600th of a degree. To put 40 microarcseconds in ordinary terms, it is roughly the angle subtended by an orange sitting on the surface of the moon. Resolving that required a telescope with an aperture the size of the Earth, which is precisely what was built. Radio dishes in Hawaii, Arizona, Mexico, Chile, Spain, and the South Pole observed simultaneously, their data time-stamped by atomic clocks and shipped physically on hard drives to be combined afterwards. The resulting virtual instrument has a resolution set not by the size of any dish, but by the distance between them, which is the diameter of the planet. Now do TON 618. Its shadow is roughly 20 times larger than M87's in physical terms, but it is around 1,000 times further away in the sense that matters for angular size. The result comes out at something on the order of 1 to 2 microarcseconds. That is not resolvable by the Earth-sized array. It is around 20 to 30 times smaller than what that instrument can currently distinguish. But notice the number. It is not a millionth of the required resolution or a billionth. It is roughly a factor of 20. Resolution improves with the separation of the telescopes and with shorter wavelengths. An interferometer with elements in space, one dish in Earth orbit and one much further out, or elements at the Earth-Moon distance, would have a baseline tens of times longer than the planet. Such missions have been proposed, and a Russian-led space interferometry mission actually flew in the 2010s, operating with one element in a highly elliptical Earth orbit and achieving baselines several times the Earth's diameter. So the shadow of TON 618 sits in a strange category, not observable, not absurdly beyond reach either. It is roughly one generation of instrument beyond what exists, in a field that has moved fast. Whether it would be worth doing is a separate question, and the honest answer is probably not on its own. But an actual image of that shadow would do something no other measurement can. It would give the mass directly from geometry, with none of the assumptions we have been cataloguing, no radius-luminosity relation, no geometry factor, no extrapolation, the size of the ring, the distance, and the formula. That is all it would take. The number that has been argued about for 20 years could in principle be settled by looking. Since we are here, and since the scale of this particular horizon makes it possible in a way that smaller black holes do not, let me take you across it, not for drama, because the arithmetic of falling into an object this large produces a genuinely unusual result, and it is one of the few places where the size of TON 618 changes not just the magnitude of what happens, but the character of it. You are outside, falling inward, not orbiting, just released. From rest, a long way out. For a very long time, nothing happens at all. Gravity accelerates you, but gravity is felt only as tidal stretching, and there is none worth speaking of. You are in freefall, which means weightless, which means the sensation is precisely the sensation of floating. The disk is somewhere off to one side, enormous and slow. If you are falling along the axis, above the plane, you see it face on. A luminous wheel, brightest at the center, and a dark circle in the middle of it that is growing. You cross the horizon. Nothing happens. There is no membrane, no flash, no threshold, no shock. Your instruments read normally. Your clock ticks at 1 second per second, as clocks always do from the perspective of whoever is holding them. The stars behind you are still there. You could still see the disk. This is the part that is hardest to accept, and it is not a subtlety or an approximation. The horizon is not a local feature. There is nothing at that radius that a passing observer can detect. It is defined globally by which paths through spacetime eventually lead outward and which do not, and that is not a property you can measure from inside a small box. An outside observer watching you would see something else entirely. They would see you approach the horizon and slow, your image reddening, dimming, your signals arriving further and further apart, until you froze at the boundary and faded to nothing. You would never, from their point of view, cross. That is not an illusion, and it is not a description of what happens to you. It is what happens to the light, which is a different question. Now, inside, what has changed is causal structure. Outside a black hole, the future is the direction of increasing time, and you can move where you like in space. Inside, the roles swap. The decreasing radius has become your future in the same sense that tomorrow is your future, not a place you can decline to visit, but a direction of time. Firing an engine does not help. In fact, it hurts. Accelerating inside the horizon shortens the proper time remaining. So the way to survive longest is to do nothing at all and fall freely. How long? For a Schwarzschild black hole, the maximum proper time from horizon to center is a simple expression, and it scales directly with the mass. For a black hole of 10 solar masses, it is about 1/10 of a millisecond. For the one at the center of our galaxy, roughly a minute. For TON 618, it is about 12 days. 12 days. Inside the horizon of a black hole, weightless, in the dark, with the disk still visible above you and nothing whatever to feel, for the better part of a fortnight. And the tidal forces, which are the thing that actually kills you, do not arrive for almost all of that. Tidal stress rises as the inverse cube of distance from the center, and you begin at 1300 astronomical units. The point at which the difference in gravitational pull between your head and your feet becomes physically intolerable, comparable to the forces that would tear a body apart, sits at a radius of something like 100,000 kilometers from the center. 100,000 kilometers sounds large. It is less than a millionth of the distance you started from. At the speeds involved at that depth, you cover it in a fraction of a second. So the shape of the experience, if you can call it that, is 12 days of nothing, followed by roughly half a second of everything. No warning, no gradient. The stretching that features in every popular account of black holes is real, and for this object it occupies the final instant of a journey lasting nearly 2 weeks. What is at the end of it? Honestly, we do not know. General relativity says a singularity. A point, or rather a moment, at which curvature becomes infinite and the theory stops producing meaningful answers. Every physicist I am aware of regards that as a statement about the theory rather than about the universe. Infinities in physics are almost always a sign that a description has been pushed past its domain, and general relativity has no quantum mechanics in it, which means it has nothing to say about matter at the densities involved. What replaces it? A quantum core, a bounce, a region of spacetime with a structure nobody has yet written down, is genuinely unknown. Not unknown in the sense of contested, unknown in the sense that there is no accepted theory of quantum gravity to consult. That is one of a small number of places in physics where the honest answer is not a range of estimates. It is a blank. One last thing about this object, which sits at the far end of time rather than the far end of space. Black holes evaporate. Hawking showed in 1974 that quantum effects at the horizon cause a black hole to radiate, very faintly, with a temperature inversely proportional to its mass. Small black holes are hot. Large ones are cold. TON 618 is about as cold as anything in the universe. Its Hawking temperature is on the order of a billionth of a degree above absolute zero. That is far colder than the cosmic microwave background, which currently sits at 2.7 degrees and still bathes everything in existence. Which means TON 618 is not evaporating at all. It is absorbing more energy from the background radiation of the universe than it emits, and it will continue to grow, very slightly, for a very long time. Only when the universe has expanded enough for the background to cool below a billionth of a degree, which takes something like 100 trillion years, a number for which we have no useful comparison, can this black hole begin to lose mass at all. And once it starts, the evaporation of an object this size takes on the order of 10 to the 100th years. The universe is currently 13.8 billion years old, which is roughly 10 to the 10th. The number above is 10 to the 100th. The gap between those is not a difference of degree. If nothing intervenes, no unknown physics, no decay of matter into something else, no collapse of the vacuum, then this black hole will be one of the last structures remaining in the universe. Long after the last star has burnt out, long after the last stellar remnants have cooled to the temperature of space, long after the galaxies have been carried out of each other's reach by expansion, there will be a slowly shrinking dark object where the center of this galaxy used to be, radiating at a temperature indistinguishable from zero, taking 100 orders of magnitude longer to disappear than the universe has so far existed. Then nothing. That is what the number describes. Now back to the question of whether the number is right. But even the smallest version is a problem, and the problem is time. 2.9 billion years. That is how old the universe was when the light we are reading tonight left the disk. It is worth pausing on what that epoch was actually like, because the early universe gets used loosely, and this is not the very early universe. This is not the first light, not the Dark Ages, not the era of primordial fog. 2.9 billion years is a fifth of cosmic history. The cosmic microwave background had already cooled from its original 3000 degrees down to about 20 Kelvin. The first stars had formed and died. Reionization, the period when radiation from the earliest stars stripped the electrons off the neutral hydrogen filling space, had been complete for well over 1 billion years. Galaxies were assembling vigorously. In fact, the universe was near the peak of its star formation history, producing new stars faster then than at any time before or since. So this is not an implausibly early moment. It is a young universe, but a working one. And in it, already fully assembled, is an object containing the mass of every star in the Milky Way. Start with the seed, because everything must start somewhere. The first generation of stars, called Population 3, formed from gas that contained nothing but hydrogen, helium, and traces of lithium. No carbon, no oxygen, no iron, none of it existed yet, because all of it is manufactured inside stars, and there had not been any. That composition matters enormously, because heavy elements are what allow gas to cool efficiently, and cooling is what allows a collapsing cloud to fragment into many small pieces rather than a few large ones. Without efficient cooling, primordial gas clouds are thought to have collapsed into stars far more massive than anything forming today, possibly 100 to 1,000 solar masses each. Such stars burn ferociously and briefly, lasting a few million years, and then their cores collapse. Depending on the exact mass, some of them leave behind black holes of a few tens to a few hundred solar masses. That is the light seed. Call it 100 solar masses, formed within the first few 100 million years. Now grow it. A black hole accreting at the Eddington limit grows exponentially, because the limit scales with mass. The bigger it gets, the more it is permitted to eat, so the more it eats, so the bigger it gets. The characteristic timescale for that growth, sometimes called the salpeter time, is around 45 million years at 10% efficiency. That is how long it takes the mass to multiply by a factor of about 2.7. Getting from 100 solar masses to 66 billion requires a factor of 660 million, which is about 20 of those e-foldings. 20 times 45 million years is 900 million years, and 900 million is comfortably less than 2.9 billion. On the arithmetic alone, there is time, plenty of it, which means the difficulty is not where most accounts put it. The difficulty is not that the sums do not add up. The sums add up fine. The difficulty is the word continuously. That 900 million year figure assumes the black hole accretes at its maximum permitted rate, without interruption, for 900 million consecutive years. Every year it does not. The clock stretches, and there are excellent reasons to think black holes do not do that. The first problem is supply. Gas has to get from the galaxy at large, from the halo, from cold streams flowing in along filaments of the cosmic web, from mergers with other galaxies all the way down to a region a few thousand astronomical units across. That is a reduction in scale of many orders of magnitude, and angular momentum fights it the entire way. Gas that starts out orbiting at galactic radii has to shed almost all of that rotation before it can reach the center. The mechanisms that do this, bars, spirals, mergers, turbulence, are intermittent and messy. The second problem is that stars get in the way. Gas flowing inward is also the raw material for star formation, and a substantial fraction of it gets converted into stars long before it reaches the nucleus. Those stars then explode, and supernovae drive gas back outward, heating it and unbinding it. The third problem is the black hole itself. This is the one that makes the whole picture awkward. The brighter the quasar shines, the more radiation pressure it exerts on its own surroundings. At high accretion rates, it can heat the surrounding gas, drive powerful winds, and blow the fuel supply out of the galactic center entirely. The engine is self-limiting. Success interrupts itself. Astronomers call this feedback, and the evidence for it is substantial. It is one of the leading explanations for why galaxies are not far more massive than they are. Put those three together and the picture that emerges is not continuous accretion but episodic accretion. Bursts, feasts, and long famines. And this is not theoretical hand-waving, it is measurable. Count how many galaxies host an active quasar at any given moment. Compare that with how many should contain a black hole capable of being one, and you get the duty cycle, the fraction of the time these objects are actually switched on. The answer is not 100%. Estimates vary with epoch and method, but the numbers that come out are typically in the range of a few percent to perhaps 10. If a black hole is only accreting hard 1/10 of the time, then 900 million years of growth requires 9 billion years of clock, and 9 billion years was not available. The universe was 2.9 billion years old. That is the actual shape of the problem, not the arithmetic. The duty cycle. There are three ways out, and they are not mutually exclusive. The first is to start bigger. If the seed is not 100 solar masses but 100,000, you need 10 fewer e-foldings, and the required growth time roughly halves. But 100,000 solar masses is not a stellar remnant. No star of that mass can exist. Radiation pressure would tear it apart before it finished forming, so a heavy seed has to come from somewhere else. The leading candidate is called direct collapse. The idea is that under specific conditions in the early universe, a large cloud of primordial gas could collapse essentially in one piece, without fragmenting into stars at all, forming a single enormous object at its center that then collapses directly into a black hole of 10,000 to 100,000 solar masses. The conditions required are quite particular. The gas must remain hot enough not to fragment, which means molecular hydrogen, the most effective coolant available in pristine gas, has to be destroyed. That requires the cloud to be bathed in ultraviolet radiation from nearby star-forming regions, strong enough to break the molecules apart, but not so close that the neighbors pollute the cloud with heavy elements. It is a narrow window. You need a bright neighbor, but not too bright and not too near. Priyamvada Natarajan at Yale has done much of the work establishing whether that window is wide enough to matter. Her models trace which dark matter halos in the early universe would have been massive enough, irradiated enough, and clean enough to permit direct collapse, and they conclude that such sites are rare but not vanishingly so sufficient, in fact, to seed the observed population of early quasars. The second way out is to break the Eddington limit temporarily. That sounds impossible, but the limit is derived for a specific idealized geometry, spherical, steady, fully ionized. Real accretion flows are none of those things. If gas arrives in a thick, dense, opaque torus rather than a thin disk, photons can become trapped in the flow and dragged inward with the gas rather than escaping to push back on it. Under those conditions, sometimes called slim disk or photon trapping accretion, simulations suggest accretion rates several times or even tens of times Eddington are possible in short bursts, most plausibly during gas-rich galaxy mergers. The third possibility is stranger and less popular, though it has never been ruled out, that some black holes were not formed from anything in the ordinary sense, but were produced directly by density fluctuations in the first fraction of a second after the Big Bang. Primordial black holes remain a live hypothesis. There is no evidence for them, and there is no evidence against. Now, and this is the point I want to land, because it is where TON 618 sits differently from most of the objects it gets grouped with. The extreme early quasars, the ones at redshifts above 7, where the universe was less than 800 million years old and black holes of 1 or 2 billion solar masses were already in place, are a seed problem. There is simply not enough time to build them from stellar remnants, and they are the strongest argument for heavy seeds. TON 618 is not that. At 2.9 billion years, there was time for a light seed to work, given continuity. What TON 618 tests is not how the growth started, it is whether the growth could be sustained. Something kept feeding this object, at high rates, for a very long stretch of cosmic time, without the feedback shutting it down and without the supply drying up. That is a statement about environment. It implies a galaxy sitting in an unusually rich node of the cosmic web, with cold gas flowing in along filaments continuously, rather than in bursts, without the kind of catastrophic merger that would disrupt the inflow. We cannot check any of that, because we cannot see the galaxy. The quasar outshines it by a factor of several hundred, and there is no confirmed detection of the host's starlight. We do not know its mass, its shape, whether it has neighbors, whether it sits in a cluster or a void, which leaves us in a peculiar position. The one object that most strongly constrains how sustained black hole growth can be is also the one whose surroundings are most completely hidden by the very brightness that makes it interesting. The James Webb Space Telescope has begun to change this picture for other objects, and the results have not been reassuring for the standard model. Since 2022, it has found a population of extremely compact, extremely red objects in the early universe, nicknamed little red dots, many of which appear to host black holes that are far too massive relative to their host galaxies by the standards of anything nearby. In the local universe, a black hole is typically around 0.1% of the mass of the surrounding stellar bulge. Some of these early systems appear to be running at 10% or more. The black holes, in other words, seem to have arrived first, and the galaxies to have caught up afterwards. The Webb results deserve more than a passing mention, because they have arrived very recently, and they are actively unsettling the picture. Since it began science operations in 2022, the telescope has found large numbers of extremely compact, very red sources in the early universe objects, nicknamed little red dots, appearing in quantity at redshifts between 5 and 9, when the universe was between about 500 million and 1 billion years old. Their spectra show broad emission lines, which is the signature of gas moving fast under the influence of a central mass. And applying the same virial machinery we have been discussing gives black hole masses in the range of millions to hundreds of millions of solar masses. That is not itself surprising. What is surprising is how those masses compare with the galaxies they sit in. In the nearby universe, the ratio is stable and small. A black hole is around 0.1% of the stellar mass of its host's bulge, a relationship so consistent that it is one of the strongest constraints we have on how galaxies and their central black holes influence each other. Some of these early objects appear to be running at 10% or more. In the most extreme reported cases, the black hole seems to contain a comparable mass to all the stars around it. If those measurements hold, then black holes did not grow alongside their galaxies in the early universe. They ran ahead. The hole came first, and the galaxy assembled around it. Two caveats are mandatory here. The first is that these masses come from the same single-epoch virial method, applied to objects even further outside its calibrated range than TON 618, and are subject to every systematic we have discussed, and probably several we have not. The second is that there is an active debate about whether the broad lines in some of these objects come from a black hole at all, or from something else entirely extremely dense gas, or a compact starburst, and the question is not settled. But if even a portion of it survives scrutiny, it changes what TON 618 means. An object whose black hole is far too massive for any plausible host galaxy stops being an anomaly requiring explanation and starts being an early member of a population. If that holds, then the question is not how TON 618 grew so large so fast. It is why we expected black holes to grow in step with their galaxies at all. And that raises a question about the number itself, which is the one this has been building toward. Because everything I have just described, the seed problem, the duty cycle, the feedback barrier, is a set of constraints on how a 66 billion solar mass object could exist. If the true mass is at the lower end of the range, most of the tension eases considerably. If it is at the upper end, some of these mechanisms stop being sufficient. The theory is being stretched by a number that is uncertain by a factor of 2.5 in either direction, which is a slightly uncomfortable thing to notice, and it leads directly to the question everybody actually wants to ask about this object, and which nobody can answer cleanly. There is one more piece of context that changes how this object should be read, and it concerns not TON 618 but the moment it belongs to. Quasars are not evenly distributed through cosmic time. They are a phenomenon of a particular era, and that era has ended. If you count how many quasars exist per unit volume of space at each epoch, which you can do, because a large survey gives you redshifts for hundreds of thousands of them, the curve is not flat, and it is not a steady decline. It rises steeply from the earliest times, peaks, and then falls away sharply. The peak sits at a redshift somewhere around 2 to 3. TON 618 is at 2.219. It is not merely an early quasar. It sits essentially at the maximum of the entire quasar population, at the single busiest moment in the accretion history of the universe. Whatever conditions favored black holes eating, they were at their most favorable then. And TON 618 is at the extreme end of the distribution, at the extreme of the epoch. And the same period has another name, because something else peaked at the same time. The rate at which the universe was forming stars not in one galaxy, but everywhere, summed over all of space, also reached its maximum, around a redshift of 2. The universe was producing new stars roughly 10 times faster then than it does now. Astronomers call that period cosmic noon, and everything since has been a long afternoon. The two peaks are not a coincidence. Both processes run on the same fuel, which is cold gas falling into the centers of galaxies, and both were operating at their maximum for the same reasons. The universe was smaller then. At a redshift of 2.2, the linear scale of everything was about a third of what it is now, which means the volume was around 30 times smaller and the average density of matter 30 times higher. Galaxies were closer together. Mergers were far more frequent. The cosmic web was denser, and the filaments feeding cold gas into galactic centers were richer and more sustained. There was also simply more gas. Star formation converts gas into stars permanently, and 13 billion years of it has used up a great deal. The galaxies of the present are, on the whole, running low. So what we are watching in TON 618 is not an anomaly against a quiet background. It is the most extreme example of a process that was, at that moment, happening everywhere, and then it stopped. The decline is steep. Between cosmic noon and now, the number density of luminous quasars has fallen by something like a factor of 1,000, not a tailing off, a collapse. There is a further wrinkle, and it is called downsizing. And it is one of those observations that quietly inverts an intuition everybody starts with. You might reasonably expect that the biggest objects took the longest to build, and therefore that the most massive black holes were the last to switch on. The opposite is true. The most massive black holes were active earliest and shut down first. The less massive ones remained active for longer, and it is the modest ones that dominate the accreting population today. The giants finished early and went quiet, which is exactly what TON 618 is showing us, an object that had already completed its assembly at 2.9 billion years, and which even then was accreting at only 5% of what it was permitted, as if the main event were already over. Look at what remains today. The black hole at the center of the Milky Way is accreting at a rate around a billionth of its Eddington limit. It is not off, quite, it flares occasionally, and it emits faintly at radio and infrared wavelengths, but for practical purposes it is dormant. If you moved a quasar to the center of our galaxy, it would be visible from Earth in daylight, and it would sterilize a good fraction of the disk. What is actually there is so quiet, it took decades to prove it existed. The nearest genuine quasar, 3C 273, the object that started all of this, is 2.5 billion light-years away. There are none nearby. There is nothing in the local group, nothing in the Virgo cluster, nothing within a distance that would be considered close by extragalactic standards. The phenomenon that once lit up the universe has retreated to a shell of distance that is really a shell of time. And Lyndon Bell's conclusion from 1969 holds. The black holes did not go anywhere. They are all still there, a supermassive black hole at the center of essentially every large galaxy, hundreds of billions of them in the observable universe, almost all of them dark. The quasar era did not end because the engines were destroyed. It ended because the fuel stopped arriving. So the universe we live in is the aftermath of the one Ton 618 belongs to. We are looking back into an epoch that was denser, wetter with gas, more violent, more collisional, and far brighter, from a position 11 billion years downstream of it, in a universe that is emptying out and slowing down. That reframes the object slightly, and I think it reframes it in the right direction. Ton 618 is not a monster that appeared against a calm background. It is the largest thing produced by a moment when the entire universe was doing this, when galaxies were colliding constantly, when cold gas was pouring down filaments into every deep well available, when star formation was running an order of magnitude faster than it does now, and black holes everywhere were being fed. We caught the biggest one, at the peak, running easily, and then the whole era wound down, and the fuel ran out. And what is left is a universe of quiet galaxies with enormous dark objects at their centers, and light from the busy period still in transit, arriving here, tonight, on detectors that were built by creatures who evolved during the afternoon. Is it the biggest? That is the question this object exists in public to answer, and it has carried the title for the better part of 20 years. It is worth taking seriously rather than dismissing, because the answer is genuinely interesting, and the answer is, nobody can tell you. Not because the data are poor, because the contenders are measured by different methods, and those methods do not produce comparable numbers. There are 4 ways to weigh a supermassive black hole, and they probe different regions, make different assumptions, and carry different systematic errors. The first is stellar dynamics. You observe the stars near the center of a nearby galaxy. Measure how fast they are moving from the Doppler, broadening of their absorbed light, and build a model of the gravitational potential that could produce those motions. This is the most direct method available for quiet galaxies. It requires excellent spatial resolution. You must resolve the region where the black hole dominates over the stars themselves, and it requires assumptions about the shapes of the stellar orbits, which are not directly observable. The second is gas dynamics. If a galaxy happens to have a disk of gas rotating around its nucleus, and if that disk is bright enough to observe and well-behaved enough to trust, you can measure its rotation curve and read off the enclosed mass. This is cleaner in principle than stellar dynamics, because gas disks are simpler than stellar orbits. It depends entirely on knowing the disk's inclination, and on the gas actually being in circular orbit rather than streaming or outflowing. The third is the correlation known as m-sigma. In the late 1990s, astronomers noticed that the mass of a galaxy's central black hole correlates remarkably tightly with the velocity dispersion of the stars in its bulge, how fast the stars are moving in random directions, which is a proxy for how deep the galaxy's gravitational well is. The relationship is surprisingly tight, which is itself a profound clue about how galaxies and black holes grow together, and it means you can estimate a black hole mass from a measurement of the bulge alone. But it is a statistical relation with real scatter, and at the extreme high end, where there are few galaxies to calibrate against, that scatter becomes large. The fourth is the single epoch virial method we spent time on earlier, the only one that works at cosmological distances, and the one with the largest systematic uncertainties. Ton 618 is measured by the fourth method. Almost none of its competitors are. Comparing them is like comparing a distance measured with a laser rangefinder to one estimated by pacing it out. Both may be right, and neither tells you which is closer to the truth. Now the contenders themselves. The most credible rival is a galaxy called Holmberg 15A. It is the central galaxy of a cluster called Abell 85, roughly 700 million light-years away, and it is one of the largest individual galaxies known a diffuse elliptical, whose outer starlight extends across more than 1 million light-years, so faint at the edges that where it ends is largely a matter of where you decide to stop measuring. What makes it interesting is the center, which is missing. Ordinary elliptical galaxies have stellar density rising steadily toward the middle. Holmberg 15A instead has a large, flat core, a wide region where the density of stars stops climbing and levels off, as though something had scooped them out. The standard explanation is that it was. When two galaxies merge, their central black holes sink toward the middle and form a binary pair, and that pair acts as a gravitational slingshot, flinging individual stars out of the core at high speed over hundreds of millions of years. The size of the resulting hollow scales with the mass of the black holes that carved it. In 2019, a team led by Kianush Mergun at the Max Planck Institute for Extraterrestrial Physics measured that black hole directly, using stellar dynamics and detailed orbit modeling. They obtained about 40 billion solar masses. That is a stellar dynamical measurement of first-tier method, applied carefully, with a well-understood error budget. It is a considerably more solid number than the one attached to TON 618, and it is lower. It is also entirely consistent with TON 618. If TON 618's true mass sits at the lower end of its range, Holmberg 15A is heavier. If it sits at the middle or top, TON 618 is heavier. The two error bars sit on top of each other, and no observation currently possible separates them. Then there is the Phoenix Cluster, a galaxy cluster several billion light-years away. It is the most X-ray luminous cluster ever found, and its center is doing something that most clusters do not, cooling rapidly. The hot gas at its core is radiating away its energy and falling inward at a rate of hundreds of solar masses per year, feeding a burst of star formation in the central galaxy that is orders of magnitude more intense than anything comparable. The black hole at the center of that cooling flow has been estimated at up to 100 billion solar masses from the properties of the surrounding hot gas. That estimate is far less direct than the others. It depends on modeling the temperature and density structure of the X-ray emitting gas and inferring the gravitational potential it must be sitting in. Most astronomers regard the figure as plausible rather than established, and the uncertainty is large. But if it holds, it beats TON 618, even at the top of TON 618's range. There are others. IC 1101, the central galaxy of the Abell 2029 cluster, has been credited with anything from 40 to 100 billion solar masses on the basis of the M-sigma relation. A figure quoted less often now, not because it has been refuted, but because applying that relation at the extreme end is understood to be unreliable. NGC 6166, a radio galaxy at the heart of another cluster, comes in at around 30 billion from the rotation of a circumnuclear gas disk, which is a more direct measurement than M-sigma and arguably more trustworthy than the virial method, though it too depends on an assumed inclination. And the club is not large. Perhaps a dozen objects have credible estimates above 10 billion solar masses. Almost all of them are at the centers of galaxy clusters. In the enormous elliptical galaxies that sit at the bottom of the deepest gravitational wells in the universe, the places where merger after merger has funneled material inward for 10 billion years. Notice what happens when you line them up honestly. 40 billion measured well, 100 billion measured poorly, 66 billion measured by extrapolation, 30 billion measured moderately well. Every error bar overlaps every other error bar. There is no ordering that the data supports. The ranking is a game played in fog. It is worth attaching a number to the phrase largest in the universe, because the phrase implies a survey that has not happened. Black holes with masses measured by direct dynamical methods, watching stars or gas, actually orbit them number somewhere around 150. That is the entire high-confidence catalogue, and every one of those objects is comparatively nearby, because the method requires resolving the region where the black hole dominates the local gravity, and that becomes impossible beyond a certain distance. Black holes with virial estimates from quasar spectra number in the hundreds of thousands, and that population reaches across most of cosmic time. But those are estimates of the kind we have spent tonight examining, each carrying the same factor of a few uncertainty, and they are useful in bulk rather than individually. The observable universe contains something on the order of 2 trillion galaxies, and essentially every large one is expected to host a supermassive black hole at its center. So the claim that any particular object is the largest black hole in the universe is a claim about a sample of a few 100,000, drawn overwhelmingly from the brightest and most easily detected members of the population, out of a total that is at least 1 billion times larger. It is not that the claim is wrong, it is that it is not the kind of claim anybody is in a position to make. What can honestly be said is narrower and, to my mind, more interesting. TON 618 is among the most massive black holes for which we have any measurement at all, and it sits close enough to the theoretical maximum that whatever governs the upper limit of black hole growth is probably operating on it. And there is a further point which cuts closer. There is good reason to think black holes cannot get much bigger than this. Several theoretical treatments Priyamvada Natarajan and Ezekiel Treister produced, an influential one, argue that there is an upper limit to black hole mass, somewhere in the region of 50 billion solar masses, set not by a hard physical wall but by the accretion process defeating itself. Above that mass, the accretion disk becomes so large that its outer regions become gravitationally unstable and fragment into stars rather than flowing inward. The black hole runs out of the ability to be fed, regardless of how much gas is available. Which places all of these objects, TON 618 included, right at or just above the theoretical ceiling. That could mean we are seeing the maximum, which would be satisfying. It could also mean the masses are systematically overestimated, which would be less satisfying and is entirely possible. And there is one piece of evidence pointing in that direction, which I find the most persuasive argument in the whole dossier. Black hole mass correlates with host galaxy mass. In the nearby universe, a central black hole is typically about 0.1% of the stellar mass of the surrounding bulge. In the most massive galaxies, the ratio runs higher, a few tenths of a percent, occasionally approaching 1%, but it does not commonly exceed that. Apply that relationship to 66 billion solar masses, and the host galaxy of TON 618 would need a stellar mass somewhere in the range of tens of trillions of solar masses. There is no galaxy like that. Not one. The largest galaxies known contain a few trillion solar masses of stars, and they are the giant ellipticals at the centers of the richest clusters. A galaxy 10 times larger than the largest known galaxy would be a remarkable object, and it would not be invisible, even swamped by a quasar. A system that size would leave signatures. There are 3 ways to resolve that, and they are all interesting. Either the ratio is genuinely different in the early universe, and black holes at this epoch ran far ahead of their hosts, which is exactly what the James Webb results on little red dots are beginning to suggest. Or TON 618 is a genuine freak, an object at the extreme tail of every distribution simultaneously. Or the mass is overestimated, and the true figure sits toward the lower end of that error bar, which would bring the host galaxy back into the range of things that plausibly exist. The third possibility is not the exciting one, but it is the one I would put money on. None of this is resolvable with current instruments, and it is worth being specific about what would resolve it. The James Webb Space Telescope has the sensitivity and the infrared reach to attempt something nobody has managed: separating the quasar's light from its host galaxy's starlight and getting a mass for the galaxy. If the galaxy turns out to be ordinary, the black hole mass is in trouble. If it turns out to be enormous, the black hole mass is supported. Beyond that, the next generation of ground-based telescopes, the extremely large telescope in Chile with a 39-meter mirror and its counterparts, all due within the next decade, will not resolve the broad-line region of TON 618. It is far too distant, and no realistic instrument will get there. But they will resolve the broad-line regions of much nearer active galaxies, and in doing so, they will finally allow the geometry factor to be measured rather than assumed. That is the real prize. The single largest source of uncertainty in the mass of TON 618 is not anything about TON 618. It is a poorly known correction term buried in the formula which could be pinned down by observing entirely different objects that happen to be close enough to see properly, which means the mass of this black hole will most likely become more precise without anyone ever pointing a telescope at it again. There is one measurement that would collapse most of the uncertainty on this specific object, and it is worth spelling out why nobody is going to make it. The systematic errors in the single epoch method all stem from the same place. The broadline region radius is being inferred from luminosity rather than measured. Measure the radius directly. By reverberation mapping, and the largest extrapolation in the chain disappears. So, run a reverberation campaign on TON 618. Monitor the continuum and the H-beta line. Find the lag, get the radius. Now consider what that requires. The lag equals the light travel time to the clouds. For an object of this luminosity, the radius-luminosity relation predicts a broad line region somewhere in the region of several hundred to 1,000 light days out, call it 2 years of light travel, in the object's own frame. But we are not in the object's frame. At a redshift of 2.219, time itself appears stretched by a factor of 3.2. A process that takes 2 years there takes over 6 years as we observe it. Every timescale is dilated by the same factor that stretches the wavelengths. So the delay you are trying to detect is on the order of 6 or 7 years. To measure a lag of 6 years with any confidence, you need a baseline several times longer. You must see the continuum vary, and then see the lines respond, and then see it happen again, to confirm the correlation is not accidental. That is a monitoring program running for 20 years or more, with a cadence of weeks, on an object at 15th magnitude, requiring infrared spectroscopy on a large telescope, because the line in question is not in the optical. 20 years of regularly scheduled large telescope infrared spectroscopy on a single quasar to produce one number. No time allocation committee in the world would approve that, and it would be difficult to argue they should. The same telescope time spent on hundreds of closer, fainter, faster varying objects produces far more science, which leaves the situation as it is. The measurement that would settle the mass of TON 618 is not impossible in principle, requires no new technology, and involves nothing more exotic than pointing an existing instrument at a known position on a regular schedule. It is simply longer than the careers of the people who would have to start it. For now, the number stands where the 2004 paper left it. 66 billion solar masses, plus or minus a factor of 2.5. One of the largest black holes ever measured. Possibly the largest, possibly not, and possibly not by a wide margin. It is worth saying what TON 618 looks like from here, now, with current instruments, because it is no longer a lonely entry in a Mexican bulletin. It has a spectrum in the Sloan Digital Sky Survey, taken as part of a program that has now obtained spectra for something over 1 million quasars. It appears in the Gaia catalogue, which has identified several million quasar candidates by their colors and their lack of measurable parallax, the modern industrial-scale version of exactly what Iriarte and Chavira were doing by eye with a microscope. What took 2 men years of plate inspection is now a classification pipeline. It is monitored photometrically, along with everything else in the northern sky, by automated survey telescopes that image the same fields every few nights. Its brightness varies, as quasars do, by a few tenths of a magnitude on timescales of months to years, which in the object's own frame is faster still, because of the time dilation we have already accounted for. That variability is the flicker that a reverberation campaign would need to track, and it is being recorded continuously by instruments doing something else. And its host galaxy has still never been seen. Not by Hubble, not by any ground-based instrument, not so far by Webb. The quasar remains a point source. Every image ever taken of TON 618, from a photographic plate in 1957 to the most recent survey frame, shows the same thing, a dot. That is the whole observational record. 70 years of increasingly sophisticated instruments, and the object has never resolved into anything. It has become better measured without ever becoming visible. The object, needless to say, is indifferent to the question. It has been shining for however long it has been shining, and the light that carries the answer left 10.8 billion years ago and cannot be updated. But the number did something that the object never could. It traveled. It left the journal, and what happened to it afterwards is a story about us rather than about the black hole. The paper appeared in a specialist astrophysics journal in 2004. Such journals are read by working astronomers and by essentially nobody else. And the paper was not about TON 618. It was a survey of the black hole masses and accretion rates of luminous quasars at high redshift, in which TON 618 was one entry among many. It contained tables of measured fluxes, descriptions of how the data were reduced, and several pages on systematic error. The mass appeared in a column, with its uncertainty listed alongside in units of dex, a logarithmic notation used by astronomers because these quantities span many orders of magnitude and which conveys nothing at all to anyone outside the field. Then the number began to move. The mechanism by which this happens is not sinister, and it is not anyone's fault in particular. A specialist paper gets summarized in a press release, or picked up in a review, or cited in a paper aimed at a broader audience. The summary is shorter than the paper. Something has to go. What goes first is always the uncertainty, because the uncertainty is the hardest part to carry. 66 billion is a headline, somewhere between 20 and 200 billion, with 66 as the central estimate of a log-normal distribution whose width is dominated by an unconstrained geometry factor, is not a headline. It is barely a sentence, and the shortened version does not feel wrong. That is the thing. It reads as a measurement. It has the texture of a fact, a specific figure, from a peer-reviewed paper by named astronomers at real institutions. Everything about it is true. It is simply missing the part that says how much of it to believe. So the number became the largest black hole ever discovered. Then, in more places than it should have, the largest black hole in the universe, a claim the original paper never made and could not have made, given that the observable universe contains something like 2 trillion galaxies and we have credible mass measurements for a few hundred of their black holes. Ohad Shemer, the lead author, is now a professor at the University of North Texas and still works on high redshift quasars. He has been consistent in interviews about the uncertainty, which is what you would expect from the person who put it in the paper in the first place. And here is the thing about that relationship between a scientist and a number they produced that I think does not get said often enough. The astronomer knows things about the number that nobody else does. They know it was derived from a single spectrum on a single night. They know which calibration was used and how far outside its tested range it was pushed. They know the geometry factor was assumed rather than measured. They know that if the broad line clouds are being partly driven by radiation pressure rather than purely orbiting, the answer comes out too high, and that if the cloud distribution is flattened and we are looking at it near face-on, the answer comes out too low. They know that these are not competing worries that cancel, they are separate, and both could be operating. None of that is doubt about the work. It is the work. The number and the knowledge of its limitations are the same object. They were produced by the same process, and they arrive together. What happens in transmission is that they are separated. The number is portable, the limitations are not. And so, a figure that a specialist would describe as our current best constraint becomes 3 or 4 steps downstream, a fact that a child can recite. That is not a failure of journalism, and it is not a failure of science. It is a property of the channel. Information degrades when it is compressed, and the first thing to go is always the part that describes how much to trust the rest. The number has an afterlife now that has nothing to do with the black hole. It lives in scale comparison videos, in lists of cosmic extremes, in children's books about space. It sits alongside the temperature of the sun's core and the number of stars in the galaxy as one of those facts people carry around. It has been recited more times in the last decade than the paper it came from has been read. And I want to be careful not to be sour about that, because it is not a bad thing. It is a good thing that people know an object like this exists. The immensity is real, the astronomy that revealed it is real, and the fact that a species on a small wet planet can point an instrument at a smear of infrared light and derive the mass of an invisible object 10 billion light-years away is not diminished by the error bar. It is what makes the error bar worth having, but it is worth holding both halves at once, and this is the last thing I want to leave you with before we let go of it. The number is a human artifact. It was assembled out of a photographic plate, a radio survey, a spectrum from West Texas, a decade of monitoring nearby galaxies, a calibration, an extrapolation, and a term that stands in for something nobody has measured. Every one of those steps could be improved, and some of them will be. The number will change. In 30 years, it will be a different number, and the version circulating tonight will look approximate in the way that the estimates of the 1970s look approximate now. The shadow is not a human artifact. Whatever radius that horizon actually has, 400 astronomical units, or 1300, or 4000, it has that radius exactly, and it had it before there was anybody to ask. It does not sit at the center of a probability distribution. It sits at the center of a galaxy. So, back to the dark, and one last time with the number. Close your eyes, if they are not already, and try to hold 1,300 astronomical units. It resists. The mind reaches for something familiar and comes back with nothing. A kilometer you can feel. A 10-minute walk, a bridge, the length of a runway, the distance to the moon you can hold as a number, though the number is already too big to be a feeling. The distance to the sun is where it starts to go. 8 minutes and 20 seconds of light, which is at least a duration you know long enough to make tea, long enough for a phone call, and still nothing you can look at. 1,300 astronomical units is not 8 light minutes, it is 7.5 light days. And that is only the radius. The whole shadow is 2 weeks across. There is no image for that. There is no comparison that helps. You cannot picture it, and neither can I. And I have been sitting with these numbers for a long time now. What you can do is accept it as true and let it sit there, which is a different kind of understanding, and possibly the honest one. And notice what it took to put it there. A plate of glass in a darkened room in Puebla, and a man moving a microscope across it, field by field, looking for dots that were the wrong shape. He did not know. He wrote down a number, 618, and moved to 619. A telescope shaped like a cross, lying in a field in the Po Valley, not moving, letting the earth turn beneath it and reading off whatever passed overhead. A cold dome in West Texas, and Marie-Helene Ulrich at a guiding eyepiece, holding an almost invisible point of light on a slit for hours so that a photographic emulsion could accumulate enough photons to show a line. 30 years of astronomers going out night after night to watch nearby galaxies flicker, so that a relationship could be calibrated that would one day be applied to something none of them were looking at. A cryogenic spectrograph on the summit of a volcano in the Pacific, and one night's exposure, and a hump in an infrared spectrum 7,000 kilometers per second wide. None of those people were building toward this. Each of them was doing the next piece of work in front of them. The chain only looks like a chain from here, and at the far end of it, 10.8 billion years of travel through space that was expanding the whole way, past and through galaxies that formed and merged and died while the light was in transit. A black hole is sitting at the center of a galaxy nobody has ever seen. It is still there. That much we can say. Black holes do not go anywhere. The disk may have run out. The quasar may have gone dark billions of years ago, its fuel exhausted, its galaxy quietly aging around it. Or it may still be burning. We will never know, because that information is on the other side of a wall we cannot cross. The universe has expanded enough since that light left that a signal sent from here tonight would never arrive. Whatever TON 618 is doing at this moment is permanently, structurally, not our business. What we have is the light that already left. It is still arriving. It arrives tonight, and it will arrive tomorrow night, at every observatory that points toward Cain's Venatici. It arrived while the Tonantzintla plate was in its holder, and it arrived every night before and since, whether anybody was collecting it or not. It has been arriving throughout the entire history of life on this planet, and the name will not change. TON 618 means Tonantzintla 618. It means the 618th faint blue object catalogued by an observatory in Puebla during a survey for peculiar stars in our own galaxy. Every element of that description is a description of a mistake. It is not a star. It is not in our galaxy. It was not peculiar in any of the ways the survey was looking for. Astronomical nomenclature does not correct itself. Once an object has a designation in the literature, the designation stays because too many papers point at it. So the permanent name of one of the most massive objects ever weighed is a record of the moment when two men looked at it and concluded, entirely reasonably, that it was nothing much. I find that a fair arrangement. The name preserves the actual history rather than the tidy one. Somebody had to find it before anybody could understand it, and the finding and the understanding were separated by 19 years and 4,000 miles. And out of that, we have made a number. 66 billion times the mass of the Sunday, give or take a factor of 2.5. An event horizon 1300 astronomical units in radius, that light needs 15 days to cross. A disk converting an Earth into light every 13 seconds, and running, even so, at a 20th of what it is permitted. 70 suns a year, disappearing. That is the number, that is the object. They are not the same thing, and now, in the quiet, you can let both of them go.